Good evening, my dear J Warriors. This is your Captain Shreyas on the Vedantu J English channel. And today in the road series, we are doing the magnetism part, the first lecture of magnetism, guys, where we are seeing the sources of magnetic field. This is the starting part of magnetism. So if this is a topic which you have not understood before, right from the basics, I will be teaching you till the advanced level, guys. So make sure you are following this channel, following this video till the end. Okay. Now, when I talk about magnetic field sources, we are going to see how field is produced around current carrying coils, wires, solenoids, toroids, and there are two primary laws, which is Biot-Savart's law and the Ampere's law, which we'll be seeing, and we'll be ending the class with how magnetic dipoles are formed and how current carrying loops can become magnetic dipoles, bar magnets basically. So that's the flow of today's session, and this is none other than your Captain Shreyas. Welcome Harborine, hi Reena Star, welcome Joseph. I hope I'm audible and visible to all of you, right? So let's begin with the class. I hope you guys are all excited, all very thrilled. Yes, show that energy till the end of the class. Keep answering theory questions. That's what we are going to go in today's lecture. Hello Reddy, Tarun, good evening. Usha, good evening. And if you have not yet marked your attendance, mark your attendance by smashing that like button down there. And yes, subscribe to the Vedantu J English channel. Also, before we go ahead, let me also remind you, in case you have forgotten to register for the MVSAT examination, which is the Mega Vedantu Scholarship Admission Test. Do it right away, right now, because a lot of prizes are there, goodies are there for participation, scholarship obviously, and getting to know where you stand. Online test is from 10th October and offline starts 29th September. But it is recommended you start registering as early as possible, because you will lose track of what things you have to do. Also keep in mind that I have also made a video on what are the type of questions which will be asked in MVSAT and other things. What is the strategy that you need to apply? So how to prepare for MVSAT, a short small video, okay, where I have told you about the pattern, syllabus, things to attempt, things to keep in mind. In general, this is a season of scholarship exams, and I want everyone to do well, because obviously you want scholarship so that you can enroll and get those goodies, and you can also get the courses at a discounted rate, right? Cool. So let's begin with the class, and let's start with the sources part. Already done. Very good, Sanju. Good evening. Hi, NN Ideas. Now, see guys, let me tell you that when we have a static charge, stationary charge, like a proton at rest, electron at rest, something like this, what does it do? It will create something called as electric field around it. That is what we have studied in the previous chapters of 12th standard. It creates electric field around it. But the moment these charges begin to move, the moment you have dynamic means charges in motion, dynamic charges, then the moment you have a charged particle which is in motion, it not only produces electric field around it, but at the same time, apart from the electric field around it, it also starts creating a new kind of field around it, and that is nothing but your magnetic field. It is nothing but your magnetic field around it. So moving charges create electric as well as magnetic fields. Stationary charges, electrostatics, basically they create only electric field. As simple as that. But there is a very interesting case in this also. Imagine you consider a nice big conductor. Imagine you consider a nice conductor of this sorts. 1 second. this is our conductor. Okay, imagine this is our conductor. Okay, I'm just showing a chunk of the conductor. Let me label it over here. So this is nothing but a conductor. Inside a conductor, there are equal amounts of positive charges and equal amounts of negative charges. I hope you guys agree with this statement. There are equal amounts of positive and negative charges inside a conductor. Correct? Now, if there is no current inside the conductor, that means no current. Basically, I can say as a whole, it is like static charges, okay, on an average. Then around it, whatever electric field is created by the positive charge will be nullified, will be cancelled by the negative charges electric field. So, do you agree with this statement? There will be no electric field around it, no electric field. There is no electric field around it, because why? The positive charge created as much field as the negative charge, so they ended up cancelling each other. Obviously, magnetic field should not be there, so I will also say there is no magnetic field also. There is no magnetic field around it. But just imagine there is current now inside the conductor. Let's say, for example, the current is going maybe like this. If let's say there is now current inside the conductor, which means the negative charges are going like this. Remember, the flow of electrons is opposite to the conventional direction of the current. So the electrons are moving like this. So now still as a whole the conductor is neutral. Because the conductor is neutral, the neutral conductor, for that neutral conductor, you will see there is no electric field around it. Because it is neutral, I will say there is no electric field around. There is no electric field around it. But what you will see, the charges are moving, so around it you will start seeing magnetic field. What you will start seeing is nothing but the magnetic field. Magnetic field is developed. Magnetic field is developed around it. So can I say as a concluding statement, current carrying wires, okay, around it, I can say that the electric field is 0. The symbol for magnetic field is not E, because then it will be confusing. So we use a different symbol, and that is B. Magnetic field symbol is B. Magnetic field is not 0. This is around it. Do you guys agree with it? So this is basically the primary source of generating magnetic field using electricity, using current. This is the theory behind it. This is the logic behind it. Hi Siva, hi Sanju, very good. Yes, in current we have stationary or dynamic charges. In current, electricity, as an average, the charges are at rest. As an average, yes, there is internal thermal collisions which happen, but average displacement, average velocity is 0. So you can say on an average it is at rest. So no net electric field is developed. Yep. Okay. So Usha, if you watch my classes every day, day by day, your confidence will go up. Day by day, if you keep developing more backlogs, your confidence will obviously go down. So every day attending a simple class as mine will cover maybe 1%, 2%, 1% portion, and slowly within 30 days, you don't know 30% of the syllabus will be done. So it's just a matter of putting those efforts consistently rather than crying about, sir, this is not done, that is not done. So please follow the classes on the ROAR series. Okay, it's just for you guys. I'm pretty sure you will be able to do it. Okay. Now, if this point is clear that, okay, sir, fine, moving charges create magnetism around it. So what about permanent magnets? What about those bar magnets? Everybody might have played with some or the other magnet at some point of time. You might be wondering, sir, there was no current, sir. I had a magnet. I have seen that it sticks on the fridge or on the metal, but I did not see any current in it. So guess what? A permanent magnet is where the current is developed due to the electrons revolving in orbits. Remember, electrons are charges, they revolve in orbits, so they form small teeny current loops inside that atom. So those teeny currents which are there inside those atoms end up producing magnetic field. So if you thought permanent magnets are way different than electromagnets where you pass a current and magnetic field is developed, well, actually at the molecular level, at atomic level, it's the exact same thing. So the fundamental thing is that moving charges are creating the magnetic field apart from the electric field. How you see it, it's completely dependent on your perspective. For a normal person, you will be like, oh, permanent magnet, I did not give any current, still there was magnetic field. Whereas you take a coil and pass some current, you will see it suddenly starts attracting nails and magnetic materials. So you will be like, oh, maybe it is an electromagnet. But actually, even a permanent magnet is an electromagnet at molecular level. Have you understood this? Is that clear? Give me a thumbs up. Give me a thumbs up. Till this point, is it clear? The difference between a permanent magnet like the ones you might have seen which get stuck on the fridges or maybe some stickers versus, electromagnet. Electromagnet is where you pass the current and zoop, it begins to attract magnetic materials. Clear till this point, everyone? Very good, Usha. If you have been following it regularly, I'm pretty sure you would have seen a lot of difference slowly if you follow it properly. And don't worry about completing syllabus. As we proceed, slowly the syllabus will get completed. But whatever is done, that should be 100%. Remember. Okay. Now, this was actually discovered by, Ørsted. So Ørsted found this particular thing, whatever I told. So this was actually given by Ørsted. So Ørsted gave this particular theory. The formula of it was given by Biot-Savart. We'll come to that, but before going there, let's understand what magnetic field is and what's the symbol, unit, etc. So magnetic field is produced by current carrying wires or magnets around you, and magnetic field has a symbol of capital B. The symbol for it, let me put, the symbol for magnetic field is capital B. The unit is Tesla. CGS unit generally Gauss, or you can say 1 Tesla is 10 to the power minus 4 Gauss. Sorry, the exact opposite. 1 Gauss is basically 10 to the power minus 4 Tesla. Okay, so which I have written right over here, right? So this is some conversion factor which you should remember. It is obviously a vector quantity, and it follows all the other rules which electric field lines follow. What do I mean by that? Let me tell you. See, imagine I have a magnetic field line like this. This is a magnetic field line. If somebody draws a tangent, to this particular magnetic field line, then along the direction of the magnetic field, if you draw an arrow mark, that shows me exactly the direction of the magnetic field at that particular location. A tangent drawn points in the direction of the magnetic field at that point, which also means that if by chance this is a magnetic field line and this is another magnetic field lines, at the point of intersection, then you will have this as well as this, both directions, which is not possible. So guys, this is not possible. What is not possible? Field lines intersecting. Field lines basically can't intersect. Field lines can't intersect because then they will have two different directions. Which one is correct, which one is wrong? You can't have that ambiguity. It has to be a unique direction. You cannot give multiple choice questions, A or B or C or D. No, it is this means this. It is in this direction. The next important thing about magnetic field lines is how, when they are crowded and when they are far away, what do they signify? So say for example, these are the magnetic field lines coming out of some magnet or some electromagnet. So I'll just put B over here. Here they are dense. Here they are not so dense. So wherever the magnetic field lines are dense in nature, I would say the field is definitely stronger. And wherever the field lines are very, very far away, they are very, very far away relative to each other, then I will say the magnetic field in that region is basically weak. Which also means if I had magnetic field lines like this, or let's say I show magnetic field lines going inside the plane of the board like this. Okay, these are basically magnetic field lines which are going inside the plane of the board. Okay, these lines are equally spaced around each other. So such a field is said to be a uniform magnetic field. This is uniform magnetic field. Whereas this situation right over here, this is non-uniform because it is becoming strong and weak. So this is non-uniform magnetic field. B stands for magnetic, right? So non-uniform magnetic field, correct. We will do dual nature of atoms in modern physics, not today. That's a separate chapter altogether. Okay. And Siva, you are in 12th, sir. Is it enough for the live classes? School, even I have special classes, so I didn't do. What do I do? I'm not sure why you have special classes. Follow one thing, bacha, because you don't have so much of time. Hardly 3-4 months are there. Follow one thing. Try to avoid, or if school is not giving you any value, try to avoid that school as much as possible. Maintain minimal attendance, and if those special classes are really good, attend there. If you find more benefit over here on YouTube, please attend the YouTube classes. Okay, spend more time practicing is what I would say. Okay, now there is one more extra thing about magnetic field. See, all these things were even valid in electric field. Electric field lines can't intersect, gravitational field lines can't intersect. Where the field lines are close, they are strong, and when they are equally spaced, it is uniform field. One thing which is unique is that magnetic field lines never start or end. They basically are always continuous loops. They are basically always continuous loops like this. So the magnetic field lines are always as loops. They basically don't start anywhere or they don't end anywhere. That is very, very important. Also, you should know that, say for example, I just told you, okay, listen, the magnetic field lines are like this, and what is then this North Pole and South Pole? Because many of you think, sir, I thought North Pole starts the magnetic field lines, South Pole ends the magnetic field lines. Well, let me ask you a simple question over here now. Say for example, I tell you, listen, this was that magnet which produced these magnetic field lines like this. Then you will say, because the field lines are coming from this side of that chunk of piece, so I will say this is probably the North Pole and the field lines are entering down inside, so this becomes the South Pole. But what if the same field lines were originating maybe from another chunk like this over here, from another chunk over here? Then you will say this is North Pole and this is South Pole. So this definition of North Pole and South Pole depends on where you are seeing that object. If this is my object, then this side becomes north. But if this is my object, then this part becomes south. So it depends completely on the object and the relative direction of the magnetic field lines. In this case, the magnetic field lines were coming here. So from the north side, we say the field lines come out, but it is not like they actually start from there. Actually, they enter from the south and they continue their journey even inside that material. they continue their journey even inside their material and they come back over here. So this north and south is relative to the direction of the field as well as the object under consideration. Is that clear? Okay. The direction of the magnetic field lines in general depends on the direction of the current, and we'll be seeing the right hand thumb rule in a bit. Yeah. Magnetic field vector is always tangential to the field line drawn to that. Yes, Anshuman, always. I think I just showed it to you right over here. I just showed over tangent over here, which was one of the first properties. Okay. In case you did not get that was the tangent, let me explicitly mention over here. It is always tangential. All these are important things which you must definitely know. Now, now let's go to something called as the Biot-Savart's law. Everybody has now a fair idea of what is a magnetic field, etc. I have also told you about the units. Now let me tell you, Tesla is a huge unit of magnetic field. Usually the magnets which you carry in your pockets or which are there as stickers, they have a typical field of 10 to the power minus 2 Tesla, 10 to the power negative 2 Tesla. Earth's magnetic field, which we all get affected by, and the compass points in the north direction, the field is just 10 to the power minus 4 Tesla. If you have heard about machines called as MRI scan, CT scan, those machines are developing very strong magnetic fields. Even those strong magnetic fields are not like too much. They are in the range of 1 Tesla to 3 Teslas. Okay, hardly anything, a few Teslas here and there. If you talk about a very dense planet, which is like formed after, explosions, okay, or collisions and things like neutron stars. These planets, which are extremely dense, they spin really fast, they are, probably formed by some extreme processes. They have extremely high magnetic fields in the order of, tens and tens of Tesla. And remember, our blood also contains magnetic materials like iron, right? Hemoglobin, hemo stands for like iron. So guys, remember, even we get affected by the Earth's magnetic field on a minute scale. It might have long-term effects. And also remember, migratory birds and so many other animals depend on the Earth's magnetic field for their navigation. Okay, so that small magnetic field is enough. So imagine a very strong magnetic field can have too many, maybe even undesirable effects. Now, let's talk about the first law, which is the Biot-Savart's law, where you might have a current carrying wire. This is your current carrying wire, and this current carrying wire produces magnetic field around it. We have just seen that right over here, a current carrying wire produces magnetic field around it, which was also proved experimentally by Oersted. No electric field around it. So then, if I am located at a place, let's say maybe over here at this particular point. At this point, I want to know what's the magnetic field. I will be like, all the elements of the wire produce a magnetic field here. I will see the contribution of each and every single part of that wire. Meaning, I will be like, okay, let me take a small element of the wire over here. The small element of the wire will be dl, and this will be a vector. This is nothing but an elemental vector in direction of the current. The current was going this way, so that's why the arrow mark is this way. If the current was coming like this, then the arrow mark would have been like this. This small element will produce a magnetic field here. So this distance definitely matters to me. If this distance was more, maybe the field will become weak. So this distance, then I will write it down as r, which is the position of that point with respect to my element. So this r is nothing but the position, okay, position vector. This is nothing but your position vector. There will be a magnetic field at that particular point. Maybe, the magnetic field is coming towards you. or away from you, doesn't matter. For now, let's say the magnetic field is like this. So this is the field due to this small element, but this element being small, the field won't be huge, it will be just dB. So this is nothing but the elemental magnetic field, small magnetic field. I hope all these terminologies are very, very clear. Okay, if you see the diagrams also, it's given in the same form even in your textbooks. You will have a wire, you will take a small element of that wire, and due to that element you will find the magnetic field at that particular location, and that will be dB, for example. So once you get dB, you will be like, sir, what do you do with that dB, sir? There will be many such elements, each element at this place, each element at this place will produce dB magnetic field. So hence the net magnetic field will be integration of dB. The total magnetic field due to the wire will be the integration, means add all the effects due to all the elements. Is that making sense? That will be the total magnetic field produced at that particular point. But then the question is, how much is this dB, sir? How much is this value? Well, this value of dB was given by Biot-Savart, and that value of dB comes out as mu naught by 4 pi. There is a constant over here. So there is going to be basically a constant over here. I'll just write it down. Mu naught divided by 4 pi. I'll explain you what this means. Then you have, yes, your IDL, current into the element, I into DL. And then you take the cross product of it. And then you basically take the cross product of it with the position vector, and then divide it with the position vector's magnitudes cube. This is the value of dB, the magnetic field produced at some location due to a small element carrying some current, R being the distance or the position of that point from that element. You might be wondering, what is this mu naught by 4 pi? This mu naught is basically called as the permeability of vacuum. Just like you had permittivity. Permittivity decided how strong the electric field can be inside a material. So if it is able to permit more, right? So that means, it's like the field will be stronger, but dielectric materials, they end up reducing the field and they permit lesser number of electric field lines. Same way, how permeable means porous a material is. So if magnetic field is able to travel very nicely, in fact it becomes strong, it is more permeable. If it does not permit, if it is not permeable, then permeability value will be less, as simple as that. So it depends from medium to medium. This value of mu naught is 4 pi into 10 to the power minus 7. 4 pi into 10 to the power minus 7. So mu naught by 4 pi, this constant is just 10 to the power minus 7. These are SI units only. These are SI units. Keep that in mind. Okay. So this is basically straightforward your Biot-Savart's law. I hope you see that there is a cross product involved over here. Yeah, you have to do vector product, cross product over here. If you notice, the DL vector was this way, position vector was that way. So if I take my right hand's 4 fingers, point it in the direction of DL, slowly rotate it towards R, the thumb is going inside. That's why the dB vector is shown with a cross symbol, because it is going inside. Same way, here also notice DL vector was this way. If I do DL cross R, DL is here, crossed with R, the thumb comes towards you, so the magnetic field should be towards you. That's how you figure out the direction of the magnetic field. Is that okay? Will we complete all the chapters today? How can we complete all the chapters today? We are completing only sources. We're just completing the sources part. Anandu. Okay? As simple as that. Great. Now that we have seen this, now that we have seen what is the direction, etc., doing this cross product is often some time consuming or confusing process in the exam also. But using the same right hand, you can avoid this cross product and you can find the direction very easily. If the current is going like this, all you do is hold that wire. Imagine this pen was the wire. Hold the wire but let the thumb point in the direction of the current. Your fingers will wrap as if they are the magnetic field lines, like this diagram shown over here. So if you point your thumb in the direction of the current, automatically you will see the magnetic field lines. They are coming from the front, going behind your hand and coming back. But if the current is going down, hold the thumb down, the fingers will wrap around you as if they are magnetic field lines. So when you point your thumb down, the curled fingers go behind the wire, come in front of you like this and go behind that wire like that. So I can say that on this side, the magnetic field is going inside. On this side, the magnetic field is going inside, but they go behind it and they come in front towards you on this side. In this situation, the magnetic field lines are going from behind and coming towards you here and go in the front and then go behind like this over here. So these crosses and dots basically show whether they are coming out or going in. Is this rule understood? Yes, this is your thumb rule. Correct, Sanju. This is much simpler than using the cross product. It simplifies. Obviously, you can just hold the wire and you are like, okay, the field lines are going like this. Okay, the field lines are going like this. Okay, it is going in, it is coming out. Okay, it is coming out, it is going in. It's very straightforward. Very straightforward. Now, if you have to calculate the magnetic field due to a long wire carrying current, okay, like I said before, you will have to obviously integrate it over here. You have to integrate all the effects of all the elements to find the net field, and each element will give this much amount of field. So we'll see that, but before that, let us solve a simple question coming up on your screen. Imagine that there is a wire, maybe like this. There is a wire like this. Oops. Yeah. And it is carrying 2 amperes of current, and there is a small element at the origin. There is a small element of 5 millimeters at the origin. Okay, the question is find, by the way, this is also given to you. Listen, this is your x-axis, this is the origin, this is your y-axis. The wire was carrying current along the y-axis. Question is find the magnetic field, find the magnetic field at 6,8. Magnetic field at 6,8 due to this element, okay. So direct application of Biot-Savart's law. So let's see how do we find it out. First, let's locate where this point is. 6,8, 6 units in x, 8 units in y, so somewhere over here. So this is that point, guys. Okay, so let me just directly draw a line which is your position vector like this, okay. Can you quickly think and tell me what might be the length of this r? Can you quickly think and tell me what might be the length of this position vector? Think about it, my dear students. Yeah, this is 6 units, this is 8 units. Guys, Pythagoras theorem. Yep. So r is basically root of 6 square plus 8 square. 6 square is 36, 8 square is 64. So this will be root of 100, which is just going to be 10 units. In this case, 10 meters. 6 meters, 8 meters. So that will be 10 meters. So this is 10 meters. Remember, this was 8 and this was 6, of course. Oh, so I know the value of R. I know the value of the current. Direction also I know. When I do the cross product, remember there will be sine theta, I dl cross R. So I need that angle between that element and this. Remember, our element will be here. Our element will be just over here, which is of 5 millimeters length. So what could be the angle between this and this? This angle will be same as this angle. This angle theta will be the same as this angle theta. And I can see tan theta is 6 by 8. Tan theta is basically 6 by 8. 6 by 8 is same as saying 3 by 4. Whose tan is 3 by 4? Obviously 37 degrees. So theta over here is 37 degrees. That also we can find out. Okay, that is done. Now let's try to find the magnetic field. So the magnetic field formula is mu naught by 4 pi magnitude wise I dl r sine theta whole thing divided by r cube. Actually over here what happens is one of the r will get cancelled out from the numerator and this will become r raised to 2. Okay, so let's start substituting everything and see what do you get. Mu naught by 4 pi. I just told you the value of mu naught by 4 pi is nothing but 10 to the power minus 7. So let's put 10 to the power minus 7 over here. The value of current is given to be 2 amperes. The small element is 5 millimeters. So 5 into 10 to the power minus 3. Sine theta is sine of 37. Remember theta is 37. Sine 37 is 3 divided by 5. Whole thing divided by r square. R was 10. We just figured it out. So this will be nothing but 10 square. Is that clear, everyone? So let's see what and all gets cancelled over here. First of all, this 5 and this 5 just got cancelled. Okay. 10 to the power 2 got cancelled over here. This will become minus 5. This minus 5 and this will become minus 12. So hence, what do I get? Is basically 2 3s are 6. 6 into 10 to the power minus 12 Tesla. Such a small field. 6 into 10 to the power minus, 12 Tesla. Is that clear? Not minus 9. Just check it out. This was minus 7. So this was 2. This will become minus 5. 7 and 5 together will make it minus 12. So that is the answer for this. So that's extremely small, just as we expected, because it is a dB value. If you ask me the direction, I will be like, okay sir, I will use the right hand thumb rule. Current is going like this. I will hold the wire pointing my thumb in the same direction. The fingers go like this. So on the right hand side, the fingers are going inside. Right hand side, the fingers are going inside. Left hand side, the fingers are coming outside. So the dB value will be in this direction. That's going to be inside. So if you talk about it in vector form, dB vector will be 6 picotesla. Pico is 10 to the power minus 12. But it is inside. So it is negative k cap. Negative k cap. Okay. So understand the negative sign has come. 6 into 10 to the power minus 12 Tesla, but that is in the k cap negative direction. Why negative k cap? Because it is inside. K cap positive will be towards you. Positive z will be towards you. Negative z will be inside. So that's the complete answer in the vector form. This is in the scalar form or the magnitude form. Clear? Is that understood? Yes, Rock, 75% plus anything? Yes, you are eligible. Yep, you are eligible. Don't worry. All right. Now, let's talk about many such elements and find out the total magnetic field due to a wire carrying current. So, I have a wire which carries current and there are many such elements and I am standing at some distance from it over here maybe. I want to find the magnetic field due to this wire which carries this particular current. Now, imagine this is a finite wire. Imagine this is a finite wire which carries current. Every element will produce a magnetic field here, so you will have to start by choosing some small elements. Small elements. Let's say this is dy because this is along y-axis. Okay, but this r is not the same as the position vector r, so let's not get confused over here. So better to put a different symbol, capital R, and the actual position vector of that point will be a variable given by small r. What is this r? Distance from the wire. Small r is the distance from the element which will keep changing. If you change the element to here, r will be obviously longer. Here it will be different. Here it will be different. So r is a variable. And then you will also have different angles over here. This will be theta and all of that. And then you will find the magnetic field due to that particular point. That particular element. That dB value will be mu naught by 4 pi I dy r divided by r cube, but that sine theta is also involved over here. But what is the angle between the position vector and the dy vector? If you notice carefully, if you observe carefully, you will see that angle over here is this whole angle, this complete angle. So this much part was 90 degree, this much part is theta. So this is theta because parallel lines, this is 90. So basically this will be sine of 90 plus theta, 90 plus theta. Everybody understood why 90 plus theta? Okay, that's the total angle between the element and the position vector. Now what happens is, this is magnetic field here due to this guy. There are so many people like that. So the total magnetic field will be integral dB. So you have to integrate this, but with proper limits, guys. So a lot of things like mu naught I and 4 pi, everything will come outside. Even one of the r's will get cancelled. You might probably left with sine 90 plus theta is basically cos theta divided by r square will be there. Okay, and maybe that dy will be there. You have to perform that integration from here to here. The limits will be basically what is this point making an angle, what is the angle made by this point, and what is the angle made by this point. So there, those extremities will be needed. So let's say I draw a line from here to here and another line from here to here. So I can say this angle is maybe alpha, this angle is maybe beta. So the end point makes some angle alpha and beta. Okay, makes some angle alpha and beta with the line which is perpendicular. Okay, the line which is perpendicular. So those will come as the limits, and when you finally solve this integration, hopefully I put the answer somewhere. Yes, the answer comes out to be mu naught I by 4 pi distance sine theta 1 plus sine alpha plus sine beta. So let me write it in those terms which I have given rather than this. This is basically r, this is sine alpha, sine beta, this is alpha, this is beta, and of course this is our r. Okay, mu naught I by 4 pi r sine alpha plus sine beta. This is the final formula which you get. Yes, yes. Okay, I hope this is clear. Yes, second quadrant cos is negative, but sine is positive. No, sine of 90 plus theta. Sine is in the second quadrant, so it will be plus cos theta. How will it be minus cos theta? All silver teacups, silver, sine, second quadrant, 90 plus theta. So sine value should be positive. It's not cos of 90 plus theta. Cos 90 plus theta is negative sine theta. Sine 90 plus theta will be positive cos theta. Okay, got it? Okay, so this is something which you must remember. Now, how to apply this formula? That is what we are going to see, and a lot of questions are there on that. But before going ahead, Let's take some two special cases of this. The special cases are infinitely long wire and a semi-infinitely long wire. What's the difference? See, over here, finite wire means there are endpoints. Infinitely long means there is no endpoint. So this pink dotted line for an infinitely long wire will go like this. Imagine that point is at infinity. So this pink line will go like this, and this point is also at infinity. So this pink dotted line will go like this. So what will be the value of alpha and beta for such a problem? What will be the value of alpha as well as beta for such a problem? Because they have to go till the end points. Think about it. Naturally, this value of alpha will be 90 degrees, and even this value of beta will also be 90 degrees. This beta will also be 90 degrees. So for an infinitely long wire, the magnetic field will be given by mu naught I. Use this formula, mu naught I by 4 pi r, mu naught I by 4 pi distance, sine of 90 plus sine of 90, 2 times sine of 90. Sine 90 is nothing but 1. So it will become mu naught I divided by 4 pi r, 1 plus 1, which is basically 2. 2 and 4 cancels. So the magnetic field here will be mu naught into current divided by 2 pi into r. That's the answer that we get. That's the special case for an infinitely long wire. Is that clear? Mu naught I by 2 pi r, because sine 90, sine 90 both were 1, 1 plus 1 is 2, 2 and 4 cancels. Infinitely long. Semi-infinitely long means you are standing on close to the end of the wire, but the other end is infinitely far away from you, or it's a very long wire, the end is not in sight. So in such a case, what happens? This angle alpha will point here. The other pink dotted line will just go here. So see what will happen, guys. Alpha 100% will be 90 degrees because this point is going there. So it's almost like 90. But the second pink line is ending over here only. What's the angle made? Beta will be basically 0 degrees. Beta will be how much? 0 degrees. Is that clear? I'm so glad, Game Slayers. Thank you for all the love and all the support. Do you understand why beta is 0 degrees? If you did not get it, let me explain it to you right over here. Imagine this point slowly starts shifting over here. What will happen? This pink dotted line will slowly fall back and collapse onto this orange line. So this angle will become 0 degree. So for a semi-infinite wire, the beta will be 0, alpha will be 90. So in such a case, what will be the magnetic field's value? Mu naught current divided by 4 pi distance is basically r, sine 90 plus sine of 0 degree. Sine 0 is 0, sine 90 is 1, 1 plus 0 is 1. So hence the magnetic field will be mu naught current divided by 4 pi r only. So that is the answer for this. This is semi-infinite, this is finite. Just remember this, that is obvious. It will be exactly half of this. Look at it. You multiply this with half, you will get this. You will get 1 by 4. Makes sense, right? If you take one wire here, semi-infinite, another semi-infinite wire here, one wire here, and the other wire here, it will become an infinitely long wire. So that's why if you multiply this with 2, you get this. That's an easy way to remember. Hello Sri Hari, good evening. Yeah. Now that this is done, okay, let's solve some questions based out of this. One more important thing regarding this. If by chance you are on this wire and you are just directly in front of it or behind it, meaning on the axis, somewhere here, or let's say somewhere over here. On that line, the magnetic field is 0 on that particular axis of the wire. Very, very important. On the exact axis of the wire, the magnetic field is 0. So let's take some numerical examples, guys. Here is the first question. Let's say we take a square like this, and this square has some current I, side length is A, Question is, find the magnetic field at the center. Find the magnetic field at the exact center. Let's do this. Okay. Now, the moment I see this diagram and I have to find the magnetic field at the center, let me just see where the center is. Well, the center is right over here. Fair enough. Next important thing, every wire will, produce a magnetic field here. And because of the symmetry, if I just find how much contribution is there from one side, if I multiply it by 4, I will get the total magnetic field. So my job has been made little simpler. Instead of finding it for everyone because of symmetry, I'll just find it for any one of the sides and just multiply it by 4. Okay, fair enough. So let me just maybe take the bottom one or maybe this one, doesn't really matter. How far am I from this particular wire? What is this R precisely? Can you guys think and tell me what is the value of R? This is R. This is also R. This is exactly the midpoint. Remember, this is the center. If that is the center, it will be the side length by 2. It will be basically the side length divided by 2. So basically it is A by 2. R is nothing but A divided by 2. Yep. Okay. All right. All right. Now, good evening, Puvarasan. Ritik, Krishna, tomorrow I have physics exam, magnetism. Thank you for taking this chapter. I'm so glad. Enjoy this class then. Now, next thing is, I will draw the end points. I'll connect the end points to the point where I want to find the magnetic field. Because I want to know what is alpha and beta. Think carefully, guys. In this particular diagram, which is like this, and then you have this thing over here. Okay, this is basically A by 2. Even this height, if this was A, this height is also A by 2. So this is a proper isosceles right angled triangle, which means this angle that you see over here must be 45 degrees. Must be 45 degrees, and the same story repeats below, which means alpha and beta both are nothing but 45 degrees. You can see that right from this small little triangle which I have shown exclusively over here. So now let's find the magnetic field due to any one of those sides and then multiply it by 4 later on. Magnetic field due to any one such side is given by mu naught divided by 4 pi r. R over here is nothing but A by 2. Currents should be multiplied. Sine of alpha and sine of beta. So sine 45 plus again sine of 45 degrees. Correct? So let's simplify this now. 2 and 4 cancels, so it will become mu naught current divided by 2 pi multiplied by A. Sine 45, 1 by root 2. So 2 times of 1 by root 2. 2 cancels, so I am just left with mu naught current divided by root 2 pi A. Root 2 pi A. That is the field due to one of the sides. But I want to find due to the entire square, it will be 4 times the magnetic field due to any one side. So multiply this by 4. So mu naught current divided by root 2 pi A multiplied by 4. 4 you can also write it as 2 multiplied by 2, which is the same as 2 into root 2 into root 2. So root 2 will cancel, root 2 will cancel. So you will get mu naught 2 root 2 I divided by pi A. That is what it is. Okay? Is that right, everyone? Anandu Madhu, I am right now in Bangalore, but born and brought up in, born in Tamil Nadu, brought up in Maharashtra. Yeah. Unfortunately, Game Slayer, those VBuddy classes can't be provided in Ekalavya because Ekalavya is a completely different program. So VBuddy can be brought, you can buy it separately from the Vedantu store. So like you're watching this class right now, I think there is the link for Vedantu store, maybe at the bottom. it's a separate thing as altogether. So I think it will be somewhere here. See, V buddy. Okay. So JEE physics. These classes are by me. All these classes. No, this girl is not teaching. I am teaching. Okay. So it's just there for 799. It's complete 11th and 12th standard syllabus. Yep. So that's where you can find it. I hope that clarity is there, game slayers. Okay. The order of the chapters that you will teach, Sarvana, I think I had given it yesterday also for the next couple of weeks. After magnetism, we'll be going back to, center of mass, rigid body. And then again, we'll be coming back to EMI. EMI. After EMI, we'll be going to, center of mass, rigid body. Then we'll do SHM, and then we'll complete the remaining waves, light waves, sound waves, waves on a string, electromagnetic waves, all of them together. Also alternating current and gravitation towards the end. Okay, that's what it will be. Right. So now that this is done, I'm pretty sure you will be able to solve this as homework. I'm going to give you this question as homework. Okay, so try it out. It's not at all difficult. I will give you some hint though. What if I tell you, you have to find the magnetic field at the center of a equilateral triangle whose side is A and the current which is going in it is basically I. Okay, so find the magnetic field at the center. Okay, it's very simple, guys. I'll give you the hint also right over here. You just drop a perpendicular. This will be the centroid, and then basically connect the ends to that centroid. That's it. You'll be able to solve it. Okay, you can figure out how much is this because I know the altitude of an equilateral triangle. So centroid divides it in the ratio 1:2. Use simple maths, you will get it. Okay, so this question is for homework. Will you be able to do this, guys? Yep, I want everyone to post the answer in the comment. Answer should be in the comment section. Answer should be in the comment section. Okay, try it out. Right. Let's go to the next question coming up on your screen. There is a wire who carries current in the negative y direction till the origin. It is bent over here and it carries current till infinity along the x-axis. So basically the current comes in from here and goes over here. I hope this is absolutely clear what this diagram refers to. Now you are choosing a point. You are basically choosing a point somewhere over here, and that point has the coordinates of 1, 1, 1, okay, or let's say we can take it 2, 2 also, no issues, 2, 2. Question is basically at exactly this point, okay, the coordinates are 2, 2, remember, that means this length is 2, even this particular length is 2. You have to find what is the magnetic field at that point. Okay, the question is find magnetic field at the point shown. It's a very different question, very nice question. Let's see how do we do it. Okay, let's think. If I find the contribution of this guy and this guy separately, I think we'll be able to do the problem. So let's solve it one by one. Let's look at this person, the wire which is carrying the current downwards. So this becomes the perpendicular distance then. So this becomes the perpendicular distance. For the time being, let me just forget that other wire. Let me just concentrate only on this wire. Let's just forget this wire for a moment now. Okay, let's just forget this. Oops. Let's just forget this wire for a moment. Let me draw line joining the endpoints till here. Oh, this is coming from infinity. This is coming from infinity. So it should be like this, which means over here, the value of alpha will be 90 degrees. This will be 90 degrees. Can somebody tell me what should be the value of beta over here? Think carefully and tell me. What should be the value of beta? Guys, this point has a coordinate 2, 2. So even this is going to be 2 units. Even this is going to be 2 units. 2, 2, this is 90 degree. So obviously this is 90, 45 and 45. Isosceles right angle triangle. So beta is 45 degrees. How many of you got it? Yep. Vikash, I have done a separate video for boards called as the derivations. If you just search on YouTube also you will get it. All derivations, NCERT, physics, Shreyas Sir, derivations, physics, NCERT, you will get the video, okay? So it is there in one single video. So now, what is the contribution of that field due to that wire, due to that one single wire? Mu naught divided by 4 pi, current divided by distance, distance being 2, sine of 90 plus sine of 45 degrees. Okay. So how much is this? 2 4s are 8. So mu naught current by 8 pi. Sine 90 is 1. Sine 45 is 1 by root 2. So that is the magnetic field due to the first wire. As simple as that. Now you will be like, okay sir, we got this much part. Now can you tell me what about the second part? Before going ahead, I would like to see what is the direction. Maybe they are cancelling, maybe they are adding, I don't know. Now this wire, if you hold the thumb down, fingers go inside over here, go behind the wire and come in front from this side. So they come in front. So if I hold the wire like this, they are coming in front from the right side of yours. So the magnetic field B1 is 100% towards you. This wire, hold the thumb like this, the fingers come towards you. That means this magnetic field is also towards you. Magnitude wise, won't it be the same? Because whatever is here, this wire will produce the same field. So guys, B1 will be equal to B2. Therefore, the net magnetic field, which is B1 plus B2, can I say it is 2 times of B1? So it will be 2 times of this whole number over here, which is mu naught current divided by, what is it? 8 pi, yes, into 1 plus 1 by root 2. 2 and 8 cancels. So I'll be left with mu naught current divided by 4 pi, and this will be 1 plus 1 by root 2. That is the net magnetic field. Is that clear, everyone? What a brilliant question it is. That's a nice question. Great, great. Very good, guys. Next question coming up on your screen. Come on, guys, let's do this. Next question. There are 2 wires which carry currents in the opposite direction. This wire carries a current of I, this carries a current of 2I, and maybe the separation between these 2 wires is given to be, let's say, D over here. D over here. Now, the question is, if I am standing at a location of, let's say, 2D from this wire at this particular point, question is to find what is the field over here. What is the magnetic field over here due to these infinitely long wires? Okay, let's try and solve this particular question. Okay, I want to find the field here. I know this wire will also contribute, even this wire will contribute. I don't know whether they will add or whether they will subtract. That we need to figure out. Hi Binesh, hi Tamil Arsan. Think and tell me whether they will contribute or whether they will try and cancel out each other. Okay, for this wire, if you hold your thumb in this direction, what will you see? The fingers are going inside over here on the right hand side, so the field will go inside. For this guy, if you hold your thumb in this direction, then you will see the field lines are coming outwards on this side, so towards you. So clearly both their contributions are opposite in nature. They may cancel, they may not cancel. There might be some residue which is remaining. There might be some remaining value. Okay. So let me find out how much it is. Who will contribute more? Obviously this has more current and it is closer, so this will be more. So this will be stronger. This point is very far away from this wire, plus the current is also less. So this will be obviously a weaker contribution. So both of them together, this one and this one together will give you the net magnetic field. So I can say that the net magnetic field will be magnetic field which is coming towards you minus magnetic field which is going away from you. Magnetic field which is coming towards you is due to the wire carrying current downwards. So the formula for a long wire is mu naught I divided by 2 pi r. If you forgot, here it is, mu naught I divided by 2 pi r. Okay, perfect. So what do we do? Where is it? Mu naught I divided by 2 pi r. What is r? R is the distance. The distance is 2d. So I'll put 2d over here. Minus mu naught, oh, but be careful, the current is also not I, it is actually 2 times of I. So I'll put 2I over here. Okay, it is 2I current. The other wire has a current of I only, 2 pi r. R for this guy is basically this distance, which is 3D. Be careful, a lot of people make a mistake over here. So a lot of numbers are common. So like mu naught I divided by pi d is a common number. This will, 2 will cancel. So 1 by 2 will remain minus 1 by 6. Take the LCM, it is 6. So it will become 3 minus 1, which is basically 2 by 6, which is basically 1 by 3. So guys, the final answer will be mu naught I divided by 3 pi d. That is the net magnetic field and that will come towards you because this will dominate, this will not. This is less, this is strong. So the stronger field will dominate. Is that clear, everyone? Yes. Aditya, it is not exactly 2 topics. I mean, there are so many applications. So just look at this. This is just starting. I mean, Biot-Savart's law. And we have just come to the straight wires. We have to do loops. After loops, then we go to Ampere's law and then we go to applications of it. There are so many things and then dipoles and all of that. So it's going to take quite some time. Okay. All right. Till this point, if everybody is clear, can we figure out the next question? Where is the field 0? Which point do you think the net magnetic field is 0? Very interesting question. Let's take each wire separately. This wire carrying current I, place the thumb in that direction. The field lines go inside over here, go behind it and come towards you on this side. They go inside like this due to this current. If you look at this current, place the thumb down, the field lines go inside over here. The field lines basically go inside over here, go behind and come towards you from this side. Now see, where are the chances of cancelling out? Here they basically add. Here they basically add. They are not cancelling. Here they cancel, here they cancel. Here they are basically opposite. Here also they are opposite. So will I get 2 places, one on this side and one on this side where the fields will cancel? I don't think so. This is very similar to those questions where you had 2 charges and you had to find which point the field is 0. Which point the field is 0. So think about it. If I am over here, I am closer to the larger current and I am far away from the smaller current. 100% they will never ever cancel. If I am closer, distance is also less, current is also more, the field will be more. This will always be less than this one. So they will never be able to cancel it. But on the contrary, on this side, you are closer to the smaller current. Current is small, so fine, you come close. This current is large, the effect will also be more. So you nullify that by going little bit far away from that wire. So there is a chance that they will cancel out in this part. They will never ever cancel on this region. Do you guys agree with it? So somewhere over here, I don't know, maybe somewhere over here, I can call it as X, the net magnetic field will be 0. So if the net magnetic field is 0 at that point, that means the contribution of magnetic field here, which is coming towards you, is exactly balanced by magnetic field which is going away and towards you. Yes, it's coming towards you. They both are nothing but cancelling. They are cancelling out each other. Cancel. Equal and opposite. They are cancelling out each other. So what is that value? Let's try to figure it out. This guy, okay, due to this current 2I, the distance is d plus x. So it will be mu naught into 2I divided by 2 pi into d plus x. Now for this guy, this current, you are just at the distance x. So it will be just mu naught into current divided by 2 pi multiplied by x. 2 pi, mu naught, current gone. So I'm just left with 1 by x over here. And on this side, what am I left with? 2 also gone. I'm just left with d plus x over here. That's it. Now it's time to solve this. Take the reciprocal. Did I do something wrong? Sorry, this 2 should have remained. My bad. This 2 should have remained because 2 pi was cancelled. This 2 I'm not cancelling. These 2 pi's. Okay, now it's fine. So this will just become 2x is equal to d plus x. Therefore, x is equal to d. That is the final answer. So if you are standing over here at a distance of d, you will see that the magnetic fields will cancel. The net field produced will be 0. And on the contrary, if you are standing over here, the fields are not cancelling. Okay. In fact, you are seeing there are some residual values. Did you love this question? Did you understand it? Can we go ahead? Everybody with me? Okay. So these were some of the very nice questions for your magnetic field due to long wires carrying current. Long wires carrying current or short wires carrying current. Semi-infinite, finite, everything was done. And this was all based on your Biot-Savart's law. So let's move. I had given you one homework also. Make sure you are solving it. Let's move ahead to the next geometry, and that is nothing but coil. Let's solve the next thing. Now, just like a wire carrying current can produce magnetic field around it, even a coil carrying current can produce magnetic field around it. It's just that it looks more beautiful for a coil. Look at this. There is a coil which is formed, the current is going like that, and you can see how beautifully the magnetic field lines are being formed. Okay, the current is flowing like this in the clockwise direction. Actually, this is a 3-dimensional diagram. The magnetic field lines are going inside, they are going from behind, turning back and again coming here. Again going from behind and again coming here. So you can see closed loops being formed. So this is how the magnetic field lines look for a coil. If you are wondering, sir, how do I know the direction, sir? How do I know the direction? Again use your right hand thumb rule. But this time, because the current is going like this, so curl your fingers in the direction of the current. Then you will see the thumb goes inside. That means the magnetic field lines are going inside. If the current went like this, then curl your fingers like this. So magnetic field lines will come outwards like that. You will be like, sir, this is Confusing, no? In this diagram, you are saying the 4 fingers are the current, but for wire carrying current, the thumb points in the direction of the current. How do I know for every geometry? Isn't it confusing? Answer is no. See, whatever is straight will be the thumb, whatever is turning will be the 4 fingers. Here, the current is going round and round, so naturally the 4 fingers will go round, so that will become the current. Here, the current is going in a straight line manner, so the thumb will become the current. So whatever is straight, that will become the thumb. Whatever is going round will become those 4 fingers. Isn't it easy to remember now? Everyone understood how to use the right hand thumb rule? Glad you liked the question, Harborine. Yes. Okay. Ritvik, post the answer in the comment section later on. Okay. We'll discuss it there. Yep. Now, there are 2 main parts of such a problem. Say for example, the magnetic field lines. The magnetic field lines will come like this. This is a coil which is carrying current. Let's say the current is going like this. So if you bend your fingers like this, you will see the thumb going this way. So the magnetic field lines are going towards the right. That's how I know the field line's direction. Any point on this central line, which is also called as the axis of a coil. What is this central line called? The axis of a coil. This point over here is the center of that coil. I should be able to find the magnetic field, number 1. Number 2, I see at the center the field lines are concentrated, so it should be very strong. As I go far away, the field lines go far away from each other, so the field becomes weak. So as you go really far on the axis, the field lines become weaker and even more weak. So it is the strongest at the center. Is that clear? Even this diagram tells you the same thing. Look at it. It is very strong over here, but as you go far away on the axis, the field lines diverge and hence it should become a little bit weaker. So I am interested as a general location, at a general location, what's the magnetic field? So let's say for example, I'm saying that, hey, I am somewhere over here. I am somewhere over here. This is the point. It has some x coordinate. Can you tell me what is the magnetic field at this particular point in general? What's the magnetic field at this particular point in general? Now, in order to do that, I will have to find the magnetic field contribution due to every single element on that wire, add up their contributions by integration, add them up, then I will get the total field. So, what happens is, observe, I've shown a better diagram. This is the same diagram, but slightly in the better way. This coil, I hope you can visualize, is in the YZ plane. Current is going like this. I am on the axis of that coil somewhere over here. To find the total field, I break the wire into small parts, dl, and due to that dl, I'll find the magnetic field. Now observe this very carefully, guys. This is very important. If I take a small element right on the top, dl like this, it should be pointing in the z direction. Just think about it, it will be pointing in the z direction. That dl at this particular location, this will be my position vector, will produce a magnetic field. So just visualize, dl is going along the z axis, I am finding the magnetic field there. I'm finding the magnetic field there. When I do dl cross r, cross product, dl crossed with r, I will get a vector going like this, not like that, not like this, but at an angle. dl is there, r is here, then that dl cross r will go up, but this is bent slightly, so dl is towards you, r is downwards, so dl cross r will go like that. Hence, that small magnetic field is in this direction. Hence, that small magnetic field dB is in this direction. Are you able to visualize this? Are you able to visualize this, everyone? Yes, it is a non-uniform field for sure. This magnetic field will now have two components. One component will be over here. I will call it dB perpendicular. And the other component is right over here, which is like this. I will call it dB parallel. Parallel to the axis, this is perpendicular to the axis. Why these two components? Just imagine there are so many such elements, there will be so many such dB vectors, and each of them will have components dB perpendicular, dB parallel. Just think about it. Just think about it now. There will be so many such components and so many such dB vectors. So actually, there will be 1 dB here, 1 dB over here, 1 dB like this, 1 dB like this, 1 dB like this, some dB over here. It will form like a cone if you visualize. All these are dBs. And their perpendicular vectors, they will be like this. 1 here, 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 1 here. Don't you see they are all basically cancelling out each other? All the perpendicular ones are cancelling out each other, whereas the ones which are parallel, one will be like this, other 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 will be like this. They are basically adding up each other, which are parallel. So that is the reason why I split it into components, because these perpendicular components will be parallel to the YZ plane. They will be equal in number. They will all cancel out. If one is here, the other will be there. If one is here, the other will be down. So they will all cancel out each other. Only the parallel components will remain to give you the net field, to give you this net magnetic field. Are you able to visualize this? Yes, correct. So now what we do? Okay, now that we understand, okay sir, they are only going to add. So how much is dB parallel? So this is theta. dB, if this is theta guys, so let me mark some more angles. This will be 90 minus theta. This will be theta. This will be 90 minus theta. So if this is theta, again, this would be theta. That is theta. This is theta. Two parallel lines intercept alternate angles, obviously. All this will be needed. So how much is the value of dB first? dB will be mu naught current divided by 4 pi. This is R, so R cube. dl is there, R is there, sine. Lot of people put theta here, that is wrong. What is the actual angle between dl and R? It is actually 90 degrees. If you notice, dl was towards you, R was like this, so strictly speaking, it is 90 degrees. It is 90 degrees, but in a inclined plane. Visualize that. It's in a inclined plane, guys. So your dl vector was here, R vector was here. So actually they are at 90 degrees with respect to each other. So this will be sine of 90. So therefore, dB will be mu naught current dl, sine 90 is 1, R and R will cancel, 4 pi R square. But I don't need dB, I just need the parallel component, because that is what is important for me. dB parallel will be dB cos of theta, dB cos of theta. That means it will be mu naught I dl divided by 4 pi R square, divided by 4 pi R square cos theta right over here. Now, what is the value of cos theta? Cos theta is adjacent side by hypotenuse. So, adjacent side is r, hypotenuse is small r. So, therefore, it will become mu naught I r divided by 4 pi small r cube, and then you have dl over here. That's your dB parallel. That's your basically dB parallel. Till this point, everybody clear? But I don't want that. What I want is the net field. So for that, I just need to add all of them. So the net field will be integral dB parallel, which is where? All these things are constants, mu naught I r 4 pi r cube, only dl is a variable. Bring all these people outside. Mu naught I r divided by 4 pi small r cube, integration of dl. You might be thinking small r is a variable, but it isn't. Look at it, all these distances are same actually. All these hypotenuses are the same, they are the side of a imaginary cone. If you imagine a cone, that is the side of that slanting length of the cone. So what is the dl going to be? What is dl going to be? Think about it. Integration of dl, dl, it's the perimeter of the circle. So which is nothing but 2 pi into r. Which is nothing but 2 pi into r. Is that making sense, guys? Yep. So now what is left is nothing but mu naught I. 2 pi and 4 pi cancels, r into r is r square. So I'm just left with 2 small r cube. But I also know what is the value of small r cube. What is the value of small r cube? Small r by Pythagoras theorem is root of r square plus x square. This was x, this was r. So therefore, this is nothing but r square plus x square whole raised to 3 divided by 2. Because of the root, that 2 is there, 3 was there from here. So that becomes your total magnetic field on the axis, guys. That becomes your total magnetic field on the axis. On the axis. Is that clear? Everybody with me? Yes, electrostatics was already done on this channel only. Check out the older videos, check out the playlist. Check out the Jungle Book. Jungle Book is there. It has an Excel sheet of all the older videos, whatever was conducted this year. It also has the PDFs, DPPs, everything is there at one place. So check that out for all the subjects. So we have found the magnetic field on the axis in general. Now I think, yes, that was done. Okay. Now, okay, let me do one thing. Let me take now special cases in this. Let me take special cases in this. See, what are those special cases? If this was our coil which carried the current, instead of going anywhere on the axis, what if I was exactly at the center? What if I was at the center? At that center, how much magnetic field would have been there? Well, if you are at the center, what will be the x coordinate? What will be the x coordinate if you are at the center? Obviously, it will be 0. At the center, this x length will be 0. So I'm just finding b over here. Okay. So one thing is very, very obvious. At the center, the x coordinate is 0. So using our old formula for the magnetic field on the axis, which was mu naught current r square divided by 2 r square plus x square raised to 3 by 2. Remember, that was that big formula which we just derived, mu naught I r square by 2 r square plus x square raised to 3 by 2. You might be like, sir, this is confusing. Yes, it is little difficult. But do you remember electric field due to a ring? Very, very similar formula. Same term was there, r square plus x square raised to 3 by 2. So that's why it becomes simple. Okay. So now if I substitute the value of x as 0, what do I get? mu naught current R square, whole thing divided by 2, R square raised to 3 by 2, because anything plus 0 is that same thing. 2 cancels, so I'm just left with mu naught current R square divided by 2 R cube. R square cancels, I'm just left with mu naught I divided by 2R. That's the magnetic field at the center of a coil. This formula looks very similar to the field formula due to a long wire. Let me go back and show that to you. Long wire, what's the magnetic field? Just keep this in mind, versus infinitely long wire. Look at this. This was at the center of the coil. Now look at this. Mu naught I by 2 pi r. The only difference is for a long wire, the pi comes. So that is something which you should be extremely careful. One simple trick which you can remember. If this is a long wire, it's not related to a circle, right? It's not related to a circle. So when it is not related to the circle, use pi. It's opposite. Actually, pi is related to the circle. This is opposite. Here, pi comes because it's a long wire, straight wire. It is not related. So pi has come. But when you have a coil like this, it is a circle. Circle is related to the number pi. So here you don't use that pi. It's exactly opposite. Cool, clear, simple. Yes. Yes, this question was asked many times in JEE. Now, there is a small modification to this. If there are many turns, if there are n number of turns are there, all you have to do is just multiply it with n. If there are 7 turns, you multiply it 7 times. Makes sense? Yeah, that's all you need to do. Now, there is another special case over here. Let me show that. Imagine you don't have a complete loop, but rather you have only an arc. You have only an arc which carries some current. This is theta. I want to find what is the magnetic field at this particular point. Magnetic field due to the arc. Such a question is not that difficult. Again, I'll tell you what you can do. Just imagine, had there been our complete loop, then the magnetic field due to the entire loop would have been mu naught I by 2r. Mu naught I by 2r, which we just did it right over here, mu naught I by 2r. But now, it's an arc. It is a part of a circle. So can I say the magnetic field due to the arc will contribute a part of the loop? In fact, there will be some kind of a fraction which is involved multiplied by the magnetic field due to the entire loop. You might be wondering, what is that fractional part? What is that fractional part which I am talking about? If this is theta for this arc, for the entire loop, the angle which will be there will be 2 pi radians, which is 360 degree. So the arc is how much part of that circle? If it is a quarter circle, it is 1/4. If theta was pi radian, 180, it is half. So if it is 60 degree, it is 1/6. So that is what I am talking about, the fraction. So actually speaking, the fraction will be theta divided by 2 pi. That's it. It is theta divided by 2 pi, and rest is history. Guys, this magnetic field due to the loop is just mu naught I divided by 2r. So this number is very important, theta by 2 pi. Got it? Yes? Is that clear? Hello anime god, long time no see. Ansuman, yes, we'll be solving one interesting question. Hold on now. Atoms will come towards the end, not now, but you can watch my older classes also. Okay, so let me just block this off for you. All right, so time to solve some questions, guys. Time to solve some questions. Okay, let's have a look. A wire bent into a loop produces field B at the center. If it's now rewound to form a loop of n number of turns, the new field will be how many times of the older field? Very nice question. Okay, very nice question. You take a wire, you bend it into a loop, you find the field. Now you rewind it to make n number of turns. What's the new field at the center? At the start, it doesn't seem very interesting because you are like, sir, all you have done is rewound it and made n loops. So won't the answer also be n times? That's what the first thought is. But then if you observe carefully, if you think for a moment, then you realize that there is a catch in this problem. See, I take a wire, maybe the length is L. I make it into a single loop. There is only one turn over here. At the center, the magnetic field will be mu naught I divided by 2r. But that radius which is there will be related to the length. In fact, that length, think about it, that length of the wire is the perimeter of the circle. So it is actually speaking 2 pi r. Therefore, r is technically L divided by 2 pi. So if I substitute that over here, it will be mu naught divided by 2. Instead of r, you put L divided by 2 pi. 2 cancels, so you will get mu naught, yes, mu naught pi I divided by L. That is what the original magnetic field is. That is what the original magnetic field is in terms of the length. 2 just cancelled, pi just went on the top. Is that fine? Now, if you take that same wire, instead of making a single turn, if you are making multiple turns, what will happen? Even the radius will change. Even the radius will change, mind it. Yes, so that's the catch and that's what creates the difference. Now the entire perimeter of this coil will be 2 pi r, but multiply it with n. That will be same as the old length of that wire. Each coil 2 pi r, n times will give me the total length of the wire which is used. Therefore, the value of r will be L divided by 2 pi and n. Now at the center, the new field will be mu naught current, but multiplied n times because there are n turns, divided by 2, but the new radius. So this will be mu naught current into n. Just seeing n and n will become n square, and notice all these things. Mu naught is there, current is there, 2 got cancelled, even pi went on the top, L was left below. This mu naught I pi by L is nothing but the old field, so I'll just put it as B. So B n square, the new field is n square times higher than the older field, n square times. Got it? Loved the question? Shall we go ahead to the next question coming up on your screen? Now, get ready for it. Next question, here it comes. There is a long wire over here. Like this. Sorry, like this. And it is bent like this. The current enters from here, exits from here, current is I, and this distance between the two wires is given to be as D. Question is, find the magnetic field exactly over here? Question is to find the magnetic field over here. This kind of question you will see in many places in PYQs, etc. Okay, let's try to solve this. I can see that there are many things which are making some kind of contribution here. One is this long wire, another wire here, and this bent wire here. Let's first take care of the straight wires first, and then let's go to the bent part. If you observe carefully, this wire which carries current, hold the thumb in the direction of the current, fingers go inside, so the magnetic field is going inwards. If you look at this wire carrying current downwards, it's going like that and going down, hold the thumb down, the fingers go again inside, so the contribution is again like this. If you look at only this particular part of the wire, the fingers are going like this, so the thumb goes inside, so again the contribution is inwards. So each part is contributing inwards, so they will all add up to give you the total field. That one thing is absolutely clear. Second thing, whatever contribution this part will give, same contribution this part will give, because the distances are same and the same current is only going over here. Okay, so one thing is absolutely clear. Magnetic field due to that long wire, okay, carrying current up, is the same as that other magnetic field produced by that long wire carrying current downwards. Both of them are going to be equal. How much will this be? You can just find it out. It's not that difficult. Guys, this is like a semi-infinite wire. Semi-infinite wire. Can you see that? You're directly in front of one of the end. The other end is at infinity. The other end is at infinity. Oh, for a semi-infinite wire, the formula is mu naught into current divided by 4 pi into the distance. Be careful, what's the distance? It is not d, it is actually d divided by 2. A lot of people forget that, they write d. So 2 and 4 cancel, so it will become mu naught I divided by 2 pi and d. So I'll just leave it over there. So I found the magnetic field due to this part as well as this part. It was this. The only thing remaining is the semicircular part. Okay. The magnetic field due to an arc, remember, is a fraction multiplied by the field due to the coil. Tell me one thing, a semicircle is how much of a circle? A semicircle is how much part, how much fraction? Semi is half, so it's exactly half of a circle, so just put half. And if there was a complete circle, what would be the field? It would be mu naught current divided by just 2r. But be careful, again the radius is not d, the radius is actually d by 2. The radius is actually d by 2. 2 will cancel, so I will get mu naught I, 2 has cancelled, divided by 2d. Perfect. So lastly, what is the net magnetic field? What is the net magnetic field? One contribution from the pink one, so this mu naught I divided by 2 pi d. The one from the blue one again, so mu naught I divided by 2 pi d. Lastly, from that arc, one on the top, so which we just figured it out, mu naught I by 2d. So if you notice, a lot of terms are common. Mu naught by 2d is common. I have 1 by pi, even current is common. 1 by pi plus 1 plus 1, which is 2. So it will become mu naught I by 2d, and this will be 2 plus 1 by pi. That's the answer. So that's the net magnetic field. That is your net magnetic field. Is that right? Clear? Understood? Very good. Excellent. It's a beautiful, beautiful question. Yes, it's a beautiful, beautiful question. Now let's take another variation, another nice question on this. Imagine there is a wire like this. It is bent like this. and it goes like this. Current goes in here, comes from here, goes around it like this, and this is given to be R. This current is I. Question is to find out the magnetic field at the center. Question is to find the magnetic field at the center. Come on, try it out. Meanwhile, I'm answering some of the doubts over here. No, magnetic properties is a separate lecture. Since it's a very trivial thing, I would suggest you to check out an older video. I have done a beautiful class on magnetic properties. You can just search over here, magnetic properties. See, if you are on the YouTube website, you can search here, but if you are on the mobile or on the iPad or something, you won't get this icon. You will have to search here, but then you will have to put the channel name or Shreyas Sir. So you can see this particular lecture, magnetic properties and lecture, properties and materials. Just check out this class. It's a beautifully explained class. All the concepts are there in this. Okay, just for this part, just check this out. Okay, cool. Right. सर मेरे भैया का वेदांतु से पीडी कर ही सिलेक्शन हो गया इसी ईयर 12,018 447 रैंक आई है एडवांस में. ओ पढ़ाई करके. ओ वेरी नाइस अजीत, आई एम सो ग्लैड. योर ब्रदर इज इन आई एम गेसिंग सम IIT or some NIT at least. I'm so happy, and I'm pretty sure your brother will be an inspiration to you also. Yeah, I'm pretty sure you will break his record as well. Okay, so take it as a challenge, break his record, and I'm pretty sure you will be doing it. Okay, right. So here in this question, what happens is, if you take the straight wire, you are directly in front of it, so the magnetic field is 0, so this part does not contribute. So there is no contribution. There is no contribution only. So ignore the flat parts, the straight parts. So the only contribution comes from this part, and that is a semicircle. So magnetic field due to a semicircular wire will be half of the total circle, which is mu naught I by 2r. So hence it will be mu naught I divided by 4r. But since the other one was not contributing, hence the net magnetic field will be mu naught I by 4r only. Neither this contributed nor this contributed, only that arc has made its contribution. Right? Everybody with me? Great. Now I have another interesting question. This is also very, very interesting. These kind of questions also do come in the examination. The current enters from here, exits out from here. This is having some radius. The question is field at the center. Field at the center is how much? How much is the magnetic field at the center of this? Now, at the start, the question seems very easy. Then it feels difficult. Then again, you realize it is easy. So there are a lot of twists and turns in this question. If you don't find this question difficult, either you have memorized the answer or you have not appreciated the concept in this question. See, what happens in this question is, if you are at the center, this line will not give any contribution here. This wire will also not give any contribution here because you are on the axis. So one thing is very clear, this as well as this, you are exactly on the axis. So on the axis of the straight wire, the magnetic field contribution is 0. So ignore the straight wires. Then you'll be like, sir, there is only one loop. So the answer is very simple, mu naught I by 2r, because it's just one single loop. Correct? That's what generally people think. But what you forget to see is actually the current is not going like this. It's entering and exiting. So it will get divided into two branches. One branch here, some current will go here, and then some current will go over here. I can call this current as I2 and I can call this particular current as, let's say, I1. Do you see that? And they will again meet over here. You'll be like, my goodness, sir, this is crazy. This is crazy. So the currents are getting divided. So this current which is going clockwise, if you turn your fingers clockwise, the thumb goes inside. So the contribution of the current number 1 is inside. Current number 2 is anti-clockwise. Curl your fingers anti-clockwise. The thumb comes towards you. So it is like this. Oh, so the magnetic field is towards you. One is inside. So they are, against each other. So I have to subtract the fields. How much is the field due to each one of them? Well, let's find that out. Magnetic field due to this part will be mu naught current divided by 2 rhymes the radius. But do not forget, this is only 1/4 of the entire loop. So I have to multiply it by 1/4. I have to multiply it by 1/4, everyone. Okay. What about this wire on the top? Magnetic field due to 1. Mu naught current divided by 2R into, this is not 1/4, this is 3/4 of the complete loop. So I have to multiply it by 3/4. This is like for an arc, you always multiply it by the fraction. Multiplied by the fraction. Okay. Right. Now, you'll be like, sir, what to do next? What is I1 and I2? I think I know I1 and I2 because they are parallelly moving. They are parallelly moving. Think about it. This much part of the wire versus this much part of the wire. Their resistances are different, and resistance is proportional to the length. Resistance is basically proportional to the length. So if you ask me what is the resistance of this guy versus this guy, if this is, for example, 3x ohms, this will be just x ohms. And in parallel circuits, I also know that the current gets divided in such a way, more resistance has less current. Basically, current is inversely proportional to the resistance. So what you will see, that the current will be divided in the ratio of, instead of 1:3, this will be 3 and this will be 1. So can you split that original current? Can you split that original current in the ratio of 1:3, guys? Can you split that original current in the ratio of 1:3? Definitely. One current will be I/4, other will be 3I/4. One with more resistance has less current. Yes, so this will be I/4 and the other current will be 3I/4. Is that right? Less resistance will have more current. So this is basically I2, this is basically I1. So just think about it. If I substitute 3I/4 here versus I/4 here, are you seeing one interesting thing in both these values? Are you seeing an interesting thing in both these values? Just think, mu naught is there, 2 is there, 3 on the top, 4 into 4 there below, R is there. Oh, both are exactly the same. Both are exactly equal, which means they end up cancelling out each other because one is in, one is out, which means that the net magnetic field is a big fat 0. What did I tell you? Initially you look at the problem, it feels easy. Then you realize, oh my God, it is actually difficult because the directions are different, currents are different, resistances are involved. But then you realize, oh my God, look at this, the answer is 0. Crazy, right? Now the best part is, any kind of questions like this, for example, instead of this, imagine the current came in like this and went out like that. So, the current will get divided like that. Or the current came in like this, and probably it went out like this. So it get divided like this. In any such case, always at the center, the magnetic field is big fat 0. Magnetic field is what? A big fat 0. Always. Not just this, but even if you take a square, or let's say I don't have the facility of a hexagon, but if I put in that effort to draw a hexagon like this, again, in all these diagrams, any point it can enter, any point on the corner it can exit out. It can enter from any corner and exit from any corner. You will always see, even for a regular polygon, the magnetic field will be 0. Magnetic field will be 0. It kind of makes sense. Like if it is valid for even a triangle square, you keep on making more and more sides of the polygon, eventually the polygon will become a circle. Okay, eventually the polygon will become a circle. So this is a very nice trick. You can solve the problem. If you see such a question in the exam, you directly mark the answer as 0 for the field. Yeah, okay. So you don't have to do all this nonsense. You don't have to do all this nonsense then. Yep. Waves is next month after SHM. All waves, electromagnetic, wave optics, everything together. So these were some of the good questions. So it's time now to go to Ampere's law. Ready for it, guys? Ampere's law. Okay. Just after Ampere's law, we will take a small break. And return. Okay. So just we'll see what Ampere's loop law is. All right. Now, in general, to find the magnetic fields due to loops, wires, etc., we had to where did it go? Integrate and stuff like that. So there is a way to avoid integration in some symmetrical cases, not every time, and you can save that integration time using Ampere's law. So if you remember, where is it? Biot-Savart's law. You need to find the magnetic field due to a small element, and then you integrate all the dBs to get the total magnetic field. So there is integration involved. Similarly, in electrostatics, you had Coulomb's law. If you had to find the net electric field, you had to integrate. The way to avoid that was Gauss' law. So Ampere's law is exactly like Gauss' law, the way Gauss' law behaves to Coulomb's law. So in fact, Biot-Savart's law is very similar to Coulomb's law, meaning you need to integrate, you need to find due to every single piece what's the field like, and then find the cumulative effect. But their processes can be avoided in certain scenarios, especially when symmetry is involved, like cylinders, spheres, straight lines, infinitely long. You can avoid that by using Gauss' law in electrostatics, and in magnetism you use Ampere's law. If you remember Gauss's law in electrostatics, you need a closed surface. You needed a closed surface. In magnetism, you don't need a closed surface. You need a closed path. Like imagine you start from a place, you are riding your bike and you come back to the same point. You might go around a circle, square, some weird thing, but you come back to the same point. That is exactly what you need. So you need a closed path. Okay. So it helps us in solving the problems in a slightly easier way. So let me show it right over here. Yep. Say for example, these are our wires which are carrying some currents. Some wires are there, they are carrying some currents, okay. You take a closed path. Now, closed path means you start from a point and come back to the same point. So let's say for example, I start from here I go like this, 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 okay, like this, and take a turn, come back, come back, come back, come back over here. So this is basically a closed path, and whenever you have a closed path, such a path is also called as an Amperian loop. It's an imaginary path or imaginary loop where you come back to the same point. Okay. Once you have chosen the Amperian path, all the wires here, everywhere, they are carrying current, they will create field at every point. So let's say somewhere here, the magnetic field is in this direction. Example. You find the magnetic field and go along that path some small distance. That small distance is basically dl. The magnetic field over there is B. And then what you do is take the dot product of the magnetic field with that small length that you travel. This is also called, this thing over here is also called as the line integral of magnetic field. Magnetic field. Why line integral? Because you are going along a line, you are going along a path, and who are you integrating? Magnetic field. So it's called as a line integral, just like you have area integral. So this is the line integral of the magnetic field. Okay. Now you keep doing this. Sorry, we have not even put integration symbol. Sorry guys, let me just put that integration symbol. Okay, so I forgot that integration symbol, or else where will that integration come? Okay, so you integrate this, but you come back to the same point. That's very important. You have to come back to the same point. Okay, so when you come back to the same point, that line integration will be having this symbol, because this is a closed path. This is basically a closed path. You're coming back to the same point, and you do this B dot dl. This closed line integral for magnetic field always comes out to be permeability into whatever current has been enclosed. This is called as your Ampere's law. This is called as your Ampere's law. Now you might be wondering, what the hell is this enclosed, sir? What do you mean by enclosed? Okay, just visualize this for a moment. I went around that, right? So maybe, yeah. Okay, I'll just use some different color. Imagine like a thin film which is surrounded by that closed path. This gray thing is like a film which is being held by that yellow dotted line, the closed path. Can you now see who is enclosed and who is not enclosed? This current is enclosed, this current is enclosed, this current is enclosed, this current is enclosed. So, I can just say these currents, maybe this is I1, maybe this is I2, maybe this is I3, maybe this is I4. All these I's are enclosed current. Just like you had enclosed charge, here you have enclosed current. Who is not enclosed? These currents which are outside. I1, which is outside over here, or this current, I2, which is outside. So they are outside currents. They are outside currents. Is that absolutely clear? Very good. Now tell me one thing. When I write this magnetic field, is this magnetic field due to outside or inside or both? Put it up in the chat box. Put it up in the chat box. There is no exception, Umar. There is no exception for Ampere's law, like there is no exception for Gauss' law. It's just that it is convenient for symmetrical bodies. It's not like you can't apply it for non-symmetrical. It's just that it becomes too complicated. So Jungle Book is right over here. As you're watching this live video, go down in the description box and you will see join the Jungle Book. Click on this link I'm not logged in, but you can create your account, or if you have an account, use that account. It's a free account. You will be able to download the entire sheet of Jungle Book. Okay, that's what it is. Clear, Janki? EMI, I think maybe we might start, we might complete it in September itself. Yeah, AC we will probably do later on, because for AC you should know SHM and waves, because the sine, cosine, phasor diagrams come, that you can't do it without the knowledge of phasor diagrams. So EMI is a separate thing, AC is a separate thing. Cool. This is due to both inside and outside currents. There is nothing like it is only because of inside. It's both. Just like in electrostatics Gauss law, there was electric field dot area vector, and the field was due to both charges within the surface and outside the surface. All of them contribute in the field, but the integration only depends on the inside charges. Now you might be wondering, sir, this enclosed current, sir, what is the value of this enclosed current? What is the value of this enclosed current in this case? Many of you will be thinking, I just take I1, I just take I2, I just take I3, and I just take I4, and I just add them up. I1, I2, I3, I4. Wrong. The directions are going to matter over here. So how you should check the sign is, how are you going along the closed path? You are going like this. So take the fingers of your right hand, curl it. Take the fingers of your right hand, curl it exactly the way in which you are going around that path. Your thumb will automatically point in the positive direction of the current. Thumb will automatically point in the positive direction of the current. Thumb is pointing up. So I1 will be positive. Even I4 will be positive. Who will be negative? I2 and I3. So I2 and I3 will be negative. That is how you find those sum, algebraic sum of the currents. Is that clear? Right hand thumb rule. Absolutely clear. Okay. Very good. So that is your Ampere's loop law or Ampere's circuit law. Now, let me show you a very nice application of Ampere's loop law that will blow your mind. Trust me, finding the flaw is the most tricky part in this question. So observe this question very, very carefully. See, if I take a long wire, infinitely long wire, this is infinitely long wire, and it is carrying current I, and I am situated at some distance from that wire, and I want to find the field here. You'll be like, sir, I already know the formula, I know the answer. But what if I want to use Ampere's loop law, which will make the job easier, which will help me avoid integration? So what I will do, I will choose an Amperian path, meaning a closed path. So maybe I will go like this or like this. This is my path. Okay. And let's say I'm going in the anti-clockwise direction. So this would be my DL. And at every point, the magnetic field will also be like this, because I know the magnetic field lines will be also circular in nature. The magnetic field line is also circular in nature. Now if I apply Ampere's loop law, which says B vector dot DL vector cyclic integral, I should get mu naught into current enclosed. Mu naught into basically the current which is enclosed. See what happens. There is only one current which is enclosed, and that is I. There is nothing else. So if I'm going like this, this is the positive direction. So that's also going to be a positive current. So I'll just put plus I over here using our right hand sign convention. It's just going like this upwards. Perfect. B dot DL, that's the tricky part over here. What is the dot product? Both B vector and DL vector are in the same direction. So technically speaking, the angle between them is 0. So cos 0 will come when I expand that dot product. Now this b is a constant, so I can choose to bring it outside the integration. Okay, what did I just do? I just brought it outside the integration, and I am just left with integration of dl. Cos 0 happens to be 1. Cos 0 just happens to be 1. And on the right hand side, I just have mu naught I. I just have mu naught into I. Okay, so what next? So what next? B is brought outside. Simple. What is integration of dl? dl, if you add it, is the circumference. So it is just 2 pi into basically r. Shift that 2 pi r below, you will get b is equal to mu naught I divided by 2 pi r. Isn't it fascinating? I avoided any kind of integration and very easily I got the answer. Very easily I got the answer as mu naught I divided by 2 pi r. Is that clear, everyone? Understood? Okay, this is a beautiful application of Ampere's law. So I can say this is an application, okay, application of Ampere's law. Now, if this was an infinitely long, we did it. But what if it was finitely long? What if it was finitely long? So in fact, I should technically duplicate this. This was infinitely long in this case. But in the second case, it is a finite wire. It is a finite wire. That means there is an endpoint over here and here. Tell me, if I do apply Ampere's loop law, exact same procedure, I still get the same answer, but I know this should not be correct. This is actually not correct. The actual answer should have been mu naught I by 4 pi r. I should have some sine theta 1 plus sine theta 2 or sine alpha plus sine beta. But where is that sine? Where is that sine beta? I am seeing nothing over here. How is it that both for finite as well as infinite, I am ending up getting the same answer? So there must be something wrong. Many people think this is the flaw in Ampere's loop law, but it isn't. Can you tell me where have we gone wrong in the finite part? Because infinite part, there is absolutely nothing wrong. This is exactly what it should be. But for finite, this is not the correct answer. We know that. We know that. I'll show that to you over here. Where is it? See, this is the answer. This is what the answer should have been. But it isn't. What has gone wrong? Something has gone wrong. What has gone wrong is that we told that the wire is finite and we assumed the magnetic field line is circular. This is where we went wrong. See, when it is finite, how can just current enter in and just stop over here? And where is it coming from? Where is it going? There must be a circuit which is completing it. Maybe somewhere here there is a battery which is probably supplying that current, right? So current is going like this. So maybe this battery is there like this. So this battery should be supplying the current. So actually, if you see, this magnetic field is not just because of this part, it's because of the entire wire, inside, outside, everything. So assuming that the magnetic field line is circular is the wrong thing. So definitely it is not circular. Magnetic field is non-uniform. In fact, it is not uniform. So in fact, this cos 0 is itself wrong. So if this is wrong, because the magnetic field line will be going something like that maybe. So everything else after this is also wrong. So this entire thing is wrong. Got it? Where did we go wrong? We went wrong here. Just one small thing, assumption, can make the entire process go wrong. It might make you feel that Ampere's law is invalid. And why we assumed it to be circular? Because for an infinitely long wire, the end is nowhere. I mean, even if you consider a battery, the battery will be somewhere really far which will have negligible effects. But for finite wire, it will definitely have effects. So the field lines will not be circular in nature. Did you understand this? So it is not on integration, it is not anywhere else, but it is because of this external battery which creates. So even this wire outside affects the field. Outside affects the field. Clear? Very good. Now, another simple application of Ampere's loop law is, imagine a hollow tube carrying current. Tube, hollow, carrying current. Very, very interesting. It's a completely hollow tube. So if you are wondering how the current is going, let me explain this to you. The currents are basically going like this. The currents are going like this. Try and visualize this, guys. Try and visualize. It's going along the curved surface, but not circular, along the axis, parallel to the axis. So inside part is basically hollow. So if you ask me, sir, I am inside this wire, inside this tube, what should the magnetic field be inside? If I am inside this particular tube, what do you expect the magnetic field to be? Okay, if I'm inside anywhere, guys, think about it. If I consider any Amperian loop, what will happen is that inside that Amperian loop, the enclosed current will always be zero, because the currents are going from outside. I think the side view will be better, or the cross-sectional view will be better. This is the Amperian loop, and this is our tube. This is our tube, and this is our loop. The currents are going like this here. The currents are basically going here. Observe this. These are the wires. They are along the axis, along the curved surface. Nothing is there inside. So that's why it is zero. Hence, you will see the magnetic field inside anywhere will be zero. This reminds me of the shell problem of electrostatics. If you are taking a shell which is charged, inside the shell, no matter where you go, the field is zero. No matter where you go, the field is zero. Correct? Same way, if you are outside a shell, what happens? The shell behaves like a point charge, and that's exactly what happens over here also. So again, if somebody takes a big Amperian loop, and you are at some distance r, so now you are basically outside. In such a situation, the enclosed current just becomes I. So it behaves like a long wire. So if you are outside, the magnetic field will be just mu naught I divided by, remember, pi will come because it's a straight wire, pi is associated with it. So 2 pi r. So inside it is 0, but outside it is mu naught I by 2 pi r. Just like the shell, guys. Very, very similar behavior. In fact, if you draw the graphs also, you can see it is 0 inside, suddenly jumps and it follows this behavior. Clear, everyone, till this point? Absolutely clear? Cool. What if this cylinder is not hollow? What if the cylinder is not hollow? Okay, let's take that as well. Imagine this is an infinitely long cylinder, but it is a solid cylinder, solid wire, carrying current. I am interested what might be the magnetic field inside. Outside I know it will just behave like a normal wire. So if I go anywhere outside, this is my Amperian loop. Remember, the current is going like this inside this particular wire. Total current is I. So in such a case, enclosed current will be I. It will again behave like a long wire, and this is when I am basically outside. This is when I am outside. So again the formula for the magnetic field, outside is simply put mu naught current divided by 2 pi into r. R being again the distance from the center. Okay, R being the distance from the center. This is still valid for even a solid cylinder. Just like, remember electrostatics, uniformly charged solid sphere. The solid sphere again behaves like a point charge. The formula is the same, just like a point charge. Same thing happens here also. For a solid cylinder, the field is exactly like a long wire. Is exactly like that long wire. Something like even the hollow cylinder. The problem happens when you are inside. The problem happens the moment you go inside. What's the problem? Let's apply Ampere's loop law before we go ahead. So this is mu naught into I enclosed. You also have cyclic integral dot dl. Next step, this will just become dl and something will come. Maybe some cyclic integral is there. Magnetic field is also there. Now, what happens when you are inside? Let's take an Amperian loop. So I'm just going around this like this. Okay, I'm going around it like this. So if each of them is dl, inside it, assuming there is magnetic field, obviously it will never have an end or a start. It has to be closed loops. So magnetic field lines will also be circular. So if I show the magnetic field, again it will be in the direction of B only, dl only. So this magnetic field is again going to be circular in nature. Okay. So if you ask me at any point what is the angle between B and dl, the angle between B and dl is 0, so it will be cos of 0. And anywhere over here, the value of B will be same. So in the next step, I can just take B outside this particular integration and I will be just left with integral dl. If I integrate dl, assuming this is r, that will be the length of the perimeter of the circle, which is nothing but 2 pi small r. And this magnetic field stays over here as it is. So I hope you see LHS is pretty much straightforward. I'm just assuming the magnetic field lines to be circular, which is a fair assumption. Symmetry is involved. And everywhere B and dl are in the same direction. So dot product will materialize as cos 0. Cos 0 is 1. B is a constant because everywhere I am at the same distance. So B will be constant. So bring it outside. dl, if you add, it will be the circumference, which is 2 pi r. The problem happens on the right hand side, which is especially the enclosed current. With this enclosed current, I'll tell you how do you find out this enclosed current. Just look at the top view or the cross sectional view, things will become very clear. This is the top view. Okay, you have shown the Amperian loop right over here. The enclosed current is actually only this much, whatever is there over here, not the entire thing. But at the same time, you should also remember current is flowing everywhere inside of this, This much part of the current, I'm not even bothered. I should be bothered only about this much part of that wire. Oh, so now it makes sense why the enclosed current won't be I, rather it will be lesser than I. How do I find that? I know one thing, the current is evenly distributed. So how about finding the current per unit area? That will probably give me the answer. If you take the entire cross section, which probably might have a radius of capital R, the total current I is divided on an area of pi r square. Pi r square, remember this is your R, right? This entire thing is your R. But I want only the current in this much part having radius small r, This is exactly equal to the current which is enclosed divided by pi small r square. Did you understand it? Current per unit area will be the same. Yes. So pi goes. So what will be the value of the enclosed current? It will be pi cancels, I into r square divided by r square. So substitute that over here. That's it. Just substitute that over here. It is I into r square divided by r square. Yep. So this will just be as it is till this point. No change at all. So mu naught I r square divided by r square. See what and all gets cancelled out. This r and this r gets cancelled out. So I will get the magnetic field as mu naught I divided by 2 pi r square into r. There is a small change and you can see magnetic field is directly proportional to r. This is like solid sphere. Inside a solid sphere, electrostatics, electric field increases linearly and then goes down inversely. If you remember, exactly same relationship was there. Correct? So if you combine both of them together, this is the graph that you will basically get. So see guys, if you're inside, it is proportional to R. If you're outside, it is inversely proportional to R. The graph will look like this, proportional to R and inversely proportional to R. Cool. So I think we have done fair amount of theory as of now. We will continue with the lecture in some time. So time for some break. Okay, and make sure you're liking, okay, and subscribing. If you have not yet liked, so guys, like and subscribe. Okay, let's take a break and we'll continue with the chapter. Okay. Alright guys, let's begin with the class. I hope you guys are ready and up to speed, done with your dinner. Everyone, yes, the break time is over. Welcome back guys. Time to proceed. Yes, let's go Joseph. Hi Arun Kumar. Hi Vandana, long time. Yep. Let's begin. So till the break, we had completed Ampere's law, Biot-Savart's law, and we have seen some applications like hollow tube and even infinitely long solid cylinder. Okay, we have seen the formulas and how the graph looks like. Let's take few questions before we proceed ahead. What if I tell you that, listen, there are two coils which are placed side by side. This coil has a current of I, but this coil has a current of, let's say, 3I, and their axes are the same. Even the radius is the same. Let's say the radius is given to be R and RH. The question is, if this is your x-axis, this is origin, this is y-axis, this distance is given to be R, even this distance is given to be R. Question is, what is the magnetic field at the origin? What is the magnetic field at the origin? These are two coaxial coils. Okay. Now, when you see this problem, you should understand that you have to treat these coils separately and study their effects separately and maybe then add their effects at the end. Correct? Everybody agrees to this? Now, when you thought about this, also think whether their effects will actually add up or will they be opposite to each other. Okay. So for this coil, the current is going like that. Take the four fingers of your right hand, make it go like this. You will see the thumb going left. That means the magnetic field lines are going towards the left side. So due to the current carrying I, the magnetic field is in 100% this direction. Okay. Now look at this coil. The field lines, the current is coming towards you. Curl the fingers of your right hand this way. The thumb goes this direction. So 100% the magnetic field lines due to the wire on the right hand side is going this way. Obviously they are opposite. So therefore, can I not say this total magnetic field at that origin, this has more current, so the contribution will be more, will be nothing but the value of B2 which I get minus the value of B1. B2 minus B1, B2 is the field due to the current of 3I, B1 is the field due to the current of I. Both are opposite, but B2 will be more because more current is there obviously. Now you just have to use the formula for the magnetic field on the axis. What's the magnetic field formula on the axis? In case you have forgotten, let me remind that to you. It was exactly this: mu naught I r square by 2 r square plus x square. X is the distance from the center to the point. This r is the radius. Okay. So, going down, B2 value will be mu naught into the current, which is 3I, into the radius, which is just r square, divided by 2 into r square plus x. X is basically this distance, which is itself r. So plus r square, whole thing raised to 3 by 2. Next thing over here is negative. B1 is due to this current. So mu naught into just that current, radius square divided by 2, radius square plus x is this distance, which is also r, whole thing raised to 3 by 2. From what I can see, there is 3 number over here, there is 1 number over here, 3 minus 1 is 2. So I think I should be left out with the number 2 over here 3 minus 1 is 2. 2 mu naught I r square whole thing divided by 2 times r square plus r square raised to 3 by 2. Now r square plus r square is basically technically 2r square whole thing raised to 3 by 2. This 2 and this 2 will cancel out. So I will get this 2 and this 2 will cancel out. Numerator is mu naught current into r square whole thing divided by mu naught current into r square whole thing divided by. This is 2 raised to 3 by 2. 2 raised to 3 by 2 into r square raised to 3 by 2. I'm just splitting the powers. 2 raised to 3. What is 2 raised to 3, guys? 2 raised to 3 is 8. 8's root. So root of 8. This is basically r raised to 3. R square will cancel. So I'll be left with mu naught I divided by r. Root of 8 is 2 root 2. So that's the magnetic field at the origin. Correct? That's the magnetic field at the exact origin. Clear? Hello Harborine, welcome back. Beautiful question. Such questions can come in the JEE exam. Next one on your screen now. A wire of radius A carries current of I. Question is, find the magnetic field at number 1, 2a distance from the surface of a wire, second, at a depth of a by 2 from the surface. These are the two questions. Now the moment you look at this question, a wire of radius A carrying some current I, finding the magnetic field at a distance of 2a from the surface, that is outside, and a by 2 inside. So you should think about this question or this theory which I just gave you. When you are inside, it is proportional to r. When you are outside, it is inversely proportional to r. Basically the formula has changed. This is for internal points, this is for external points. Is that right, everybody? Okay. So let's see what values will we substitute in both these questions. Now, this was our wire. It had a radius of A. If you are at a distance of 2a from the surface, technically you are at a distance of 3a from the axis. So if I want to find the magnetic field outside, the formula is mu naught current divided by 2 pi into r being the distance from the axis. Current is I only, r is nothing but 3a. Hence the answer for this question is mu naught I by 6 pi a. That is when you are outside. Mu naught I by 6 pi. But what happens when you are inside? The depth given is a by 2. So if this much is a by 2 from the axis, obviously if this is a by 2, this is also going to be a by 2. And when you are inside, the formula goes like this: mu naught I divided by 2 pi radius of that wire square multiplied by the distance from the axis. Distance from the axis comes in the numerator. So mu naught I 2 pi, distance from the axis, how much is it? It is basically a by 2. Radius of the wire is basically a, so a square. A cancels, 2 2s are 4. So mu naught I divided by 4 pi a. That is what you will get inside. So I have found both outside as well as inside, which was a direct application of nothing but this particular formula. Correct? So this formula we have applied. Clear, guys? Understood? Clear? Shall we go ahead to the next question? Next concepts? Yep. Now that we have studied some basic applications, let's improve our applications and let's go to the next application of Ampere's loop law, where we applied for a solenoid and a toroid. Now, what is this solenoid and a toroid? See, if you just take a single loop carrying some current, then the magnetic field probably might look like this. It goes like this, goes like this, comes from here, goes in like that. This is how the magnetic field lines look like. But imagine you have many turns but not on the same plane, in different planes. Imagine the current goes in like this. And this continues, guys. Oops. Many such turns are there, something like this. This are basically coils adjacent to each other. This is a single coil. These are many coils placed close to each other in different planes. That is basically called as a solenoid. This is your popular electromagnet. 100% you would have seen somebody doing it as a science project. They take a nail and they wind a coil on it, and they connect that coil or that wire to a battery. And when you pass that current, you will see that coil which is wound on that nail, okay, it behaves like an electromagnet. It starts attracting things. And this is also used for lifting heavy loads at a port, maybe a ship port. So these metallic containers are there. So what happens is that magnet, electromagnet, goes close to that metallic container. You turn on a switch, current moves, and that current, magnetizes that core inside, which then begins to attract all the magnetic material. So the container gets stuck to it. And then you can lift it anywhere, and you want to leave it. So you turn off the current, that's it. The electricity goes, the magnetic field goes, and you will release that container. So this is the functioning of an electromagnet. It can be used for pick and drop applications, solenoid applications, so many things are there. Okay, so that's a solenoid. So how would the field look like for a solenoid? They will enter from here, they will travel through the solenoid, and then they will probably exit like this. They will enter from here, okay, they will enter from here, go like this, and come out like that. So this is probably how the field lines would look like for a solenoid. If you take this solenoid, which is a hollow tube on which a coil is wound, but you bend that tube itself, just imagine somebody bends that solenoid like this. So, your wires are like this. Looks like a worm, maybe a tapeworm or something. So you will see that the magnetic field lines probably might come like that, might go in from here. Some field lines might just go like this. Some of them might just go like this. Some of them will take a longer route before entering over here. Some of them might take a shortcut from here, like that. So this is probably how the field lines will look like if you bend it, and you bend it even more, so that both these faces just touch each other. It's now a complete hollow tube. So something like this. And the coil is wound on it. Remember, both the faces now touch each other. There is no end or beginning. That's it. These are the turns of that coil. So now you will see that the magnetic field is just trapped inside. It can't go outside. It is just going to be trapped inside. Is that right, everyone? So the magnetic field is just going to be inside, guys. And such a device is then called as a toroid. What is it called? It is just called as a toroid. So from a coil, many coils adjacent to each other, solenoid. You bend that solenoid, you get a toroid. And I'm interested in how much field is there inside a solenoid and a toroid. because it has many applications. So I want to know that. Okay, so we'll just study toroid because we don't know. Sometimes they might ask a question in JEE Advanced, and there are so many entrance tests. Some syllabus has it, some syllabus does not have it. So better to learn it. It's not a difficult thing. You can see it's a toroid is a bent solenoid. So it's nothing great. It's the same thing. Now the magnetic field due to a solenoid, if you want to find it out, magnetic field due to a solenoid. Let me show you the cross section of a solenoid. So this is probably the cross section of a solenoid. What happens is the magnetic field lines inside are almost going to be parallel like this, are almost going to be parallel here. But as they reach near the ends, they begin to diverge and they will slowly go out like this and come over here. Slowly go out like this and come over here. This is how the magnetic field lines look like for a solenoid. This is the cross-sectional view. This is a pretty long solenoid. This is a pretty long solenoid. If you notice, the field lines when they go out, they are very, very far away from each other. They are not close as they were bundled inside. So 100% the magnetic field outside the solenoid is not much. In fact, it is practically zero. So this is one important thing which you must remember. Magnetic field outside the solenoid is just a big fat zero. But inside it is there, and we can find it out using Ampere's loop law. Using Ampere's loop law. So maybe I go around a part of that solenoid like this. This is the Amperian path I take. This is your Amperian path which I have taken. So if I show it to you closely, it will look like this. This is the Amperian path which I have chosen. Now observe guys carefully. Let's say the length is L. Let's say the height is H. The current flowing in it is I. Oh sorry, not like that, my bad. The current is going in this orange part, that is that thickness of that solenoid's wall. Correct? This solenoid which is there, if you cut it like that, the top part which you are seeing, the wires are going in and out. So you will probably see some wires over here. These are the wires. These are, each of them are windings. Each of them carries current I. So if you ask me how much is the enclosed current, how much is basically the enclosed current inside this Amperian loop, I will be like, listen, if I know how many turns are there and how much current is there, I think I can figure it out. Each point is current I multiplied by the number of turns. Now I don't know how many turns are there. So I'll do one thing. I will just divide it by something called as turns per unit length. Multiply it by length again. It's one and the same thing. Divide and multiply. This number of turns per unit length is given by small n, which is a property of a solenoid. A solenoid might have 1000 turns in 1 meter, 2000 turns in 50 centimeters. So how many turns are there per unit length is given by small n multiplied by the length, which is obviously L over here. So this is your I enclosed. Now let's apply our Ampere's loop law and see what do we exactly get. So cyclic integral B dot dl is equal to mu naught into I enclosed. The best part about this is when you do this B dot dl, B is not even there everywhere. Here it is 0, here it is not there. Only in this part it is there. Only in this part inside you can see the magnetic field lines are there. Oh, so when I do this integration for that entire loop, I just have to end up doing for only this side. Other parts, it is not even there. Magnetic field does not even exist. So cyclic integral B dl, and in this part, magnetic field and length are in the same direction. So angle is 0. So put cos 0 is equal to mu naught. Enclosed current is nothing but INL. Okay. B is constant. So bring it outside. So it will become B integration of dl is equal to mu naught INL. What is integral dl? Only for this particular side. Only for this particular side, the integration of dl, if you add it, it is just L. So hence, what you get is BL is equal to mu naught INL. LL will cancel. So the magnetic field which you get inside the solenoid is mu naught Ni. Very important formula again. This is inside. Outside it is 0, inside it is mu naught Ni. Is that clear? Yes. Very good. Now, there is something which I'll tell you, which is beyond this, which can come in JEE Advanced. Very rarely in JEE Mains, but it can come in JEE Advanced and maybe as a tough question in Mains. What if the solenoid is not long enough? Maybe it is a short solenoid, something like this. Then what happens? The field is not uniform inside. Sorry, the field is not uniform inside. Observe this now. You can see the field slowly becomes strong, weak as it goes out. The field has different intensities as it enters and exits out. It's roughly constant here, but if it is very long, it is okay. But if it is short, then you cannot neglect it. So in such cases, what you do is, this is the formula, guys. You want to find the magnetic field at any location, right? You want to find the magnetic field at any location. Let's say this point. You mark that point and just draw some dotted lines from here to here, and then from here to here, and then drop a perpendicular, and then drop a perpendicular over here. What did I do? Draw dotted lines till the ends and drop a perpendicular. Is that clear till this point? Okay. What is the next step? The next step is mark this angle, maybe this is alpha. Mark this angle, maybe this is beta. This might probably bring back some memories of finite wire. Exactly, it is the same, guys. The formula comes out to be, instead of mu naught Ni, it will be mu naught Ni by 2, and here you have sine alpha plus sine beta. That's it. That's the modification. This is valid for a finite solenoid, finitely long or basically short solenoid. What happens is, as a special case, if it's a very long solenoid, for a very long solenoid, alpha and beta both will be 90 degrees. So the magnetic field will become mu naught by 2 Ni sine of 90 plus sine of 90. Both are 1, so 1 plus 1 is 2. So it will just become mu naught Ni, which is approximately constant throughout for a long solenoid. But for a short solenoid, this is the formula which you will have to use. Is that okay, everyone? Is it clear? What happens if you go to one of the ends of a long solenoid? If you are at the end of a long solenoid, What do I mean by the end of a long solenoid? It means something like this. This is a very long solenoid and I am somewhere over here. Then what happens? One of the angle will be 0, the other angle will be 90 degree. Just imagine this point to be here, then alpha, this particular angle, when you reach over here, it will be 0, whereas this angle will be 90 degree. So guys, what happens is alpha becomes 0, beta becomes 90 degree. So the magnetic field becomes mu naught Ni by 2 sine 0 plus sine 90. Sine 0 plus sine 90. 0 plus 1 is 1. So it will just become mu naught Ni by 2. This is the magnetic field at the end of the solenoid, somewhere over here. This is for a long solenoid again. Okay, keep these pointers in mind, especially this one and this one. Very rarely it can come, but if it comes, you should not waste your time deriving this. You should directly write it down. Okay, so for a long solenoid, it is just mu naught Ni, but for a short solenoid, this is the formula. As simple as that. I will write. See, for example, the question says a solenoid has a length of 6 meters and radius 5 millimeters with 2000 turns carrying 1 milliampere current. Find the magnetic field in the middle. Find the magnetic field in the middle and at the end. Both the places you have to find the magnetic field. Look at these dimensions. You might be wondering, why is it even given to me? Do I have to use the formula of a finite solenoid? What do you think? Do we need to use the formula for a finite solenoid because length, radius, everything is given? Actually, if you think carefully, 6 meters, what just happened? 6 meters is very long as compared to 5 millimeters. The solenoid will look like this. It's that thin and long. So guys, I feel this is like a long solenoid. So you don't have to break your head so much. So it's like a long solenoid. It's just like a long solenoid. Don't have to worry. So we can just use the formula. Magnetic field inside somewhere at the middle will be just mu naught Ni. Mu naught is 4 pi into 10 to the power minus 7. Number of turns per unit length. There were 2000 turns for a total length of 6 meters multiplied by the current, which is 1 milliampere, which is 10 to the power minus 3. So if you notice what is happening over here, this 2 will go with this 6, it will become 3. So I'll get 4 pi by 3 over here, minus 7 and minus 3, but this plus 3. So this will just make it 10 to the power minus 7 Tesla. So that's the magnetic field somewhere in the middle, 4 pi by 3 into 10 to the power minus 7. Is that right? What about at the end? The magnetic field at the end is whatever is inside the whole thing divided by 2. You'll be like, sir, where did you get that from? Right from here, mu naught Ni by 2. So whatever is in the middle, exactly half of it is what I get. So that's why it should be this number, 4 pi by 3 divided by half, 10 to the power minus 7. So it will be 2 pi by 3 into 10 to the power minus 7 Tesla. That is at the end of the solenoid. Cool, everyone? Yeah. So these are some solenoid related problems where you generally get some calculation. Okay, listen, this is the current, this is the number of turns, find the field and all of that. Now you might be wondering, sir, what about the toroid? Correct? I'm pretty sure you might be thinking, what about the toroid? Like I explained to you before, a toroid is a bent solenoid. That means whatever magnetic field lines I might see over here, whatever magnetic field lines I might see over here will be just like the one in the solenoid. No difference at all. So, can I not say that this magnetic field of a toroid is the same as that of a solenoid, and inside a solenoid the field is mu naught Ni. That's it. If you want, you can write N as total turns upon total number of turns upon the total length of the solenoid. Now the length of the solenoid here is the circumference of the toroid. So if by chance I know this is the radius of the toroid, then I will just divide it by 2 pi this r, and that's about it. That will be the magnetic field of a toroid. As simple as that. Is that clear, everyone? Okay. So let me also block this for all of you. This is the magnetic field of a toroid, which is just like a solenoid. You can still use mu naught Ni, but if you don't like N, you can put total turns. Okay, please remember here N stands for total turns, whereas small n is the number of turns per unit length. So small n is for per unit, whereas capital is for the total number of turns. Okay, it's one and the same thing. Look at this. This is how a toroid looks. Is that right? Cool. So now most of it is done. Now we'll come to the ending part of this particular chapter, which is got to do with magnetic moments. How do they come and how much is the magnetic moment, etc. Okay, so let's talk about magnetic moments now. So very, very important topic. Understand this properly. See, if I take a coil which carries some current, I told you, listen, it produces magnetic field around it. This is how it produces magnetic field around it. And if you stand anywhere on the axis, we know that the value of the magnetic field on the axis is going to be mu naught current radius square divided by 2 r square plus x square. Because the field lines come from here and they are going in from here, it's like an electromagnet. So I can imagine instead of this, just a normal bar magnet, but this is north pole, this is south pole, because I can see the field lines just exactly behaving the same way. I can see the field lines behaving exactly the same way. Now this is nothing but a bar magnet, but also a magnetic, it's a magnetic dipole. Why dipole? Because there are two polarities, north pole and south pole. So, and they are magnetic in nature, hence magnetic dipole. This is the north side, this is a south side. So here this is actually an electromagnet, or rather I can say it's a coil carrying current. A coil which carries current behaves like an electromagnet. A coil which carries current behaves like an electromagnet. And that electromagnet has polarities, and that polarities make it look as if it's a dipole. Till this point it is clear. So coil carrying current is like an electromagnet, which means it's like a magnetic dipole. How much is this dipole moment, you might ask? How much is this particular dipole moment is what you might ask. Now I'll do one thing. Let me go to a far away point. If I am really far away on the axis, then my value of x will be much larger than the radius. Imagine I am so far away, this length is much larger as compared to the radius. So x is much larger than r, which also means x square will be more prominent as compared to r square. So I can completely ignore r square in front of, I can completely ignore r square in front of x square. By the way, I forgot 3 by 2 over here, writing it now. So therefore, this will now approximately become, look at the symbol change, approximately mu naught current into r square, whole thing divided by 2, ignore this in front of this, it will be x square raised to 3 by 2. Okay, what happens next? Then this will become mu naught I r square, 2 and 2 cancels, it will become 2x cube. This somewhat reminds me of electric dipoles. This somewhat reminds me of electric dipoles, guys. Try to recollect. In an electric dipole, the field on the axis is inversely proportional to the cube of the distance. I can see very similar things happening over here. But right now, it's not in the form of the dipole moment. So I will probably do something about it. So how about writing mu naught by 4 pi deliberately? Because I wrote 4 pi, only with that 2 was there, I have to multiply by it by 2 pi. So 2 times I times pi times r square, the whole thing divided by x cube. You'll be wondering, why did I do that? Because this is a constant, fair enough. X cube is the distance from the center, okay. Usually remember that number 2 comes whenever you are talking on the axis. Field on the axis of a dipole is 2 times the field on the equator. So that is why that 2 has come. So what must this be? Let me remind you of our old electrical dipole moment formula on the axis. It used to be 1 by 4 pi epsilon naught. Then you had that number 2 and then you had x cube and you had electrical dipole moment. This was the formula, which means whatever I have written down over here, I pi r square, that must be dipole moment but for magnetism. So I will just write this as mu naught divided by 4 pi 2 times divided by x cube. This magnetic dipole moment is what is here. So where m is nothing but I pi r square, where m is I pi r square, current into pi r square. What is pi r square? It is the area. So it is nothing but current multiplied by area. Perfect. What if there were more turns? If there were many turns in this, imagine this had n number of turns. Everywhere in this formula, you would have seen n. Here also, you will see n. So basically, I will say it is nothing but current multiplied by area multiplied by the number of turns. This m over here is basically called as the magnetic moment. So we have found a new quantity called as the magnetic moment, which is current into area into number of turns. Is that absolutely clear, guys? A new physical quantity. This quantity is also a vector quantity. Just like electrical dipole moment was a vector, magnetic moment is also a vector. It will again go from south to north direction. If this is probably the, let's say, the coil's plane, the magnetic moment will always be perpendicular to it. The magnetic moment will always be perpendicular to that area which is there. So that is why you will see magnetic moment will be NIA, okay, and it will always be in the perpendicular direction of that area. Till this point, is it absolutely clear? Let me know. So, if I have a coil like this, this is the area enclosed. There will be a magnetic moment like this. There is area, there is some current. The magnetic moment will be here. This is always going to be perpendicular to the area. Remember, there will be a north side and a south side. It will always go from south to north. Okay, so this magnetic moment is a vector perpendicular to the area of the coil and from south to the north pole, from south to the north pole, which also means all the other formulas which we studied during electrical dipole moment are still valid over here. So if this is my magnetic moment and I am at some random location somewhere here, etc. If I am somewhere over here, let's say this is R, this is, let's say, theta. At this particular point, I can find out, at this particular point, I can find out how much is the magnetic field, and that magnetic field will be given by mu naught by 4 pi. If you remember, in electricity it was electric dipole moment. Instead it will be nothing but magnetic dipole moment divided by r cube, and then you will have 3 cos square theta plus 1. This is the thing. If you are on the axis, then theta will be 0. If you are at the equator, then theta will be 90 degrees. So 0 degrees is also fine, or 180 degrees. So 0 this side or that side. So if you have forgotten, let me also remind you, this was your axis, this was your axis, and this line over here was your equator. So if theta makes 90 degrees, you are on the equator. Theta makes 0 or 180, you are on the axis. These same formulas which you studied in electric dipole moments are still valid. Yeah, I hope this is very clear. Okay, let me just block this for all of you. Great. Now let's solve some questions based out of this. A circular loop carrying current is reshaped into a square. Find the ratio of nu is to old magnetic moment. That's the question. Find the ratio of the nu is to old magnetic moment. You had a circular loop and now it has been converted into a square. Loop. What happens in this process? Current has not changed, number of turns has not changed, it is the area which has changed. Definitely. And we just saw that magnetic moment magnetic moment obviously is nothing but number of turns into current into area. That was the basic formula of magnetic moment. So neither the turns changed nor the current changed, but the area could have changed in this reshaping process. That is why the magnetic moment has changed. So can I then say that let me just find out the area, but in this process one thing did not change, and that is the length of that particular loop did not change. In the case of the square, the length of the loop, if the side length is a, it is nothing but 4 times of a, whereas for the circle the length of that loop will be 2 pi r, where this is the radius. If you ask me what is the area of that circle, it will be just pi r square. If you ask me what is the area of that particular square, I'll just say it is a square. Okay. Now since we all know magnetic moment is Ni and into area, these numbers being constant, can I say the magnetic moment of the square upon magnetic moment of the circle is area of the square upon area of the circle? Area of the square upon area of the circle. What is the area of the square? It is just a square. What is the area of the circle? It is pi r square. Now you'll be like, okay sir, answer is done. No, I do not know a and r. It is not given in the question. If it is not given, it should not be even there. What do I do? Look at this. Look at basically this expression and see what you can do. Just rearrange these terms. Just put, or rather keep a on the top only. Bring this r guy over here. What do I get? This 4 and 2 cancel, 2 will be remaining. So bring that 2 below. Pi is there as it is over here. Let that pi stay. 2 and 2 cancels, 2 remains here. Bring that 2 here. Pi remains, r goes below, a stays on the top. So a by r is pi by 2. So a by r is basically pi by 2. So just substitute that. So 1 by pi is there. Instead of a by r, you put pi by 2 and square it. So pi square and pi cancels. 2 square is basically 4. So that is the ratio. So the ratio is pi is to 4. So the new magnetic moment is to old magnetic moment is pi is to 4. Got it? Yep. Is that absolutely clear? Everyone? Yep. Pay attention on the class, guys. Very good. Let's do next question on your screen. There is a circular loop having magnetic moment of m. If it is bent along the diameter in 2 perpendicular planes, the new moment is, what is the new magnetic moment? That is the question. What is the new magnetic moment? Very interesting. Let's try this out. So we have a coil like this. It has its own magnetic moment, fair enough, and that magnetic moment is given to be m. Now what happens is I bend it along the diameter. Now when I bend it along the diameter, maybe it looks something like this. It's little difficult to draw, but I will try my best. See if you are able to visualize this. And it was bent along the diameter. It was bent along the diameter. Are you able to visualize that? So it was like this, I bent it like that into two perpendicular planes. Now I'll be like, okay, fine, this looks interesting. I'm able to visualize it, but what next? Okay. When I did that, I can think this part of the loop has some magnetic moment, this part of the loop has some magnetic moment. Let me make you visualize this. Let me make you visualize this. Just divide this loop into two halves. Just divide this loop into basically two halves, one here and one here. This part becomes vertical. That means it is this one right over here. And that other part still stays horizontal, which is exactly this part. Each of these halves will have their own magnetic moments. Like this would be m by 2. And even this would be how much? M by 2. Together it makes capital M. Together it makes capital M. So when you bend it, this magnetic moment goes this way and the other magnetic moment stays intact like this. Wait a minute. I know magnetic moments are vector quantities. So if I have a magnetic moment like this and other magnetic moment like this, the net magnetic moment will be in this direction, which will be m by 2 root 2 times. Pythagoras theorem. So guys, the final answer is capital M divided by root 2. So that's the new magnetic moment. It's a very fascinating way of solving the question. Is that absolutely clear? Everybody with me? Understood how we did it? We broke it into two halves, calculated the individual ones, reoriented it. We know it is a vector, did vector addition, we got the new magnetic moment. A very beautiful question. Now, what if I tell you there is a charged particle which is revolving in a circular path, something like this. Imagine this is a charged particle. It is going in a circular path like this. With some angular speed omega, the charge is q, and let's say the radius is also given to be r. Because it's a charge which is moving, can I not consider it like a current in a loop? Obviously, why not? Is like a current in a loop, in a conducting wire which is bent. So I can just say, hey, listen, this is exactly like this, where you show some current flowing in it. There is no difference at all. This is one and the same thing. But how much is that current and why are we doing this? The reason why we are doing this is because when a charge rotates, it creates or it makes you feel that it is a current carrying loop. And we just know current carrying loop, what does it have? It has its own magnetic moment. It behaves like a magnet. So at the end of the day, this is just nothing but a magnet. This is nothing but a magnet. This is nothing but a magnet with some polarities, north pole and south pole. So this is a magnetic dipole. This is nothing but a magnetic dipole with some magnetic moment in it. So we can find that out if I know the current, and trust me, it is not that difficult. Starting off with the current calculation. Current is how much charge flows per unit time. If I wait for one time period, the charge which goes is Q. But wait a minute, the value of time period is given by 2 pi divided by omega. Hence it is q omega divided by 2 pi. That's the value of the equivalent current which has exactly same effects as this rotating charge. But we also know there is magnetic moment. There is magnetic moment. We can find that particular magnetic moment using the formula number of turns into current into area. What is the number of turns? It's going around once, so 1. What is the current? We just figured it out. It was q omega divided by 2 pi. What is the area? It is nothing but pi r square. Cancel that pi and pi. You will be left with q omega r square divided by 2. That's the magnetic moment. Is that right, everyone? Magnetic moment is q omega r square by 2. Great. What next? I am not satisfied at all till this point. So what I will do, let me get rid of this. So I found out that the magnetic moment is q omega r square whole thing divided by 2. I will do one more thing over here. How about finding the angular momentum? Angular momentum. There is a very interesting thing that will happen. The angular momentum L will be m into r into v, but we know velocity is omega r, so it is just going to be m omega r square. It is just going to be m omega r square. Now I'll do one thing. I will divide the angular momentum and the magnetic moment, and I will see one magic happening. Angular momentum below. So I'll put all these numbers, m omega r square, magnetic moment on the top, which has q omega and r square, obviously by 2 is also there. Omega omega r square cancels. So I get magnetic moment by our angular momentum is, mass is there over here, q is there on the top, and that number 2 is remaining. I got a very specific interesting number which is independent of the radius, and it is also independent of the speed. This ratio which you are seeing right over here is not just for a charged particle, but it is found to be the same for even big bodies, even spheres, cubes, anything. This ratio is basically called as the gyromagnetic ratio. Gyromagnetic ratio. Very important concept. Magnetic moment by angular momentum is q divided by 2m. Now you'll be like, sir, where do I use this? Just imagine this is a very This is a very interesting thing. Imagine you have a charged rotating sphere. So just imagine this. This is crazy. This is a sphere and it is completely charged. It is completely charged. Like this. Okay, it's completely charged like this. And this is basically rotating with some speed. This has some mass. The total charge is q. This rotating sphere is exactly like a bar magnet, with some north pole and south pole, and believe me, it also has its own magnetic moment. We can find what is that magnetic moment of, just imagine, just a charged sphere. It is rotating, it is behaving like a magnet. It's crazy. Just a rotating sphere, it's behaving like a magnet. How do I find that? Use this formula. This is not just for point charges, but even for rigid bodies, rotating bodies. So just use this. M divided by L is q divided by 2m. Therefore, magnetic moment is charge divided by 2 times mass into the angular momentum. Now, what's the angular momentum of a sphere? It's the moment of inertia of a sphere multiplied by omega, I omega. Angular momentum is moment of inertia into omega. So, it will become Q divided by 2m. For a sphere, it is 2 by 5 mr square. And then you have that omega as it is. 2 cancels, cancels. So, you are left with qr square omega and just that 5 remains. So, that's the magnetic moment. Q omega r square by 5. So, a rotating solid sphere behaves like a bar magnet of magnetic moment Q omega r square divided by 5. Is that absolutely clear, everyone? Amazing, right? Great. So, we have seen gyromagnetic ratio. We have seen how coils produce magnetic field, behave like electromagnets or bar magnets. We have seen the formula for magnetic dipole moment. That was the last part of this particular, lecture. After this, the second part will be the effects where you study QV cross B, IL cross B, and torque and forces on magnetic moments. Okay, so we'll do the effects part in the next lecture. This lecture, we have completed the sources of field and the magnetic dipole moment concept. Okay, I hope you enjoyed this lecture. I hope you had fun. I hope you learnt a lot and a lot of new things, new tricks. If you have done that, quickly smash that like button and subscribe to the Vedantu JEE English. Okay, take care guys. Have a great time. Hasta la vista.